Welcome to the Samsung AI Forum 2020. I am Young-sang Choi, a Vice President of Samsung Electronics. The Day 1 program of Samsung AI Forum 2020 is hosted by Samsung Advanced Institute of Technology with the theme AI Technologies for the Changes in the Real World. Due to the COVID-19, we prepared the program online. On the right side of the screen, we have our speakers connected. Hello, speakers. Hello. Many participants joined today, as you see in the left side of the screen. Hello. Thank you for joining us. The entire program is being streamed globally. We recorded presentations in advance, but the speakers will be present for the live Q&A session. We prepared 2 presentation sessions, the first one with academic professors, and the second one with researchers from industry. Between sessions, we have time for the Samsung AI Researchers of the Year program, which was established this year. We also prepared small gifts for active participants, so I hope you to be with us until the end of the program. Now, Dr. Ki-nam Kim, Vice Chairman and CEO of Samsung Electronics, will give us opening remarks.
It is my honor to open the 4th Samsung AI Forum. Good morning, good afternoon, and good evening to all of you joining us globally. The COVID-19 pandemic drastically changed how we meet each other and how we interact. But one thing is certain, our health and communities are interconnected. We wish those impacted by COVID the strength to get through this tough time. Thank you to everyone who connected and took time out of your busy schedules. I am especially grateful to our esteemed speakers whose time zone spans morning to night. In recent years, artificial intelligence has been relentlessly pursued by researchers all over the world. They showed impressive achievement in many applications such as audio-visual recognition, playing Go, and even understanding natural language, as demonstrated by GPT-3. Many people had a very high expectation towards applying AI in the outbreak of COVID-19, such as finding effective drugs or tracking the spread of the virus. While AI-based tools and solutions have been rapidly implemented, AI on its own does not provide a cure to this awful disease. That requires human behavioral commitment along with investment in healthcare. Today, we'll discuss how we can make a meaningful impact on real-world problems such as the pandemic. The impressive feature of AI I mentioned before, such as superhuman recognition performance, are based on large amount of training data, either in real or simulated form, along with the larger and larger models. However, many real-world problems, such as modeling pandemics or predicting natural disasters, raise challenges. Uncertainty brought by COVID has touched every aspect of life, its effects on health, behavior, and economies. This is inherently difficult for AI algorithms to model accurately. Some problems do have not enough training data. In other instances, the models themselves need to change as the scenario evolves. Many of these large-scale models are so computationally intensive that it is impractical to solve with current computing hardware. As Samsung is a key technology supplier to the AI ecosystem, we are very interested in these problems and have active collaborations with researchers all over the world to find right solutions. Today, we invited 6 of the most prominent and passionate professors and researchers from both academia and industry. I firmly believe that we can find inspiring thoughts from the speakers and have fruitful discussions on the present and the future of AI for the benefits to humankind. Thank you again to the speakers and audience. Now, let's begin.
Thank you, Vice Chairman. We have 3 talks in the first session. Our first speaker is Dr. Yoshua Bengio, a professor at University of Montreal, Quebec, Canada, and the scientific director of Montreal Institute of Learning Algorithms. He will give us a talk on towards discovering causal representations. The second speaker is Dr. Yan LeCun, a professor at New York University and Facebook AI Research. His talk will be on energy-based models for self-supervised learning. Dr. Bengio and Dr. LeCun received the 2018 Turing Award with Dr. Hinton. Some people say the award is the Nobel Prize of Computer Science. Lastly, Dr. Chelsea Finn, a professor at Stanford University, will give us a talk on meta-learning from few-shot adaptations to uncovering symmetries. If you have any questions during the talk, please leave them on the forum website. If your question is chosen, your questions and answers will be shown on the bottom of the screen. Now, let's watch.
Hello, my name is Yoshua Bengio, and I welcome you to this presentation of the Samsung AI Forum. Welcome to the forum. I will give you a presentation on causal representation. Hello. So today I will work with you on ideas that have been making progress in our community about causality and learning representations that can capture how the world works, which I believe are related to how humans understand the world and how they could use that understanding to reason in a conscious way. So to get us started on this topic, I think it's good to try to consider the sort of thoughts we have, sort of knowledge we manipulate with our thoughts, the kind of variables that we manipulate with our thoughts and with language. So I call these variables semantic variables. And the kind of dependencies that exist between those variables is actually pretty particular. So what I'll be talking about today is part of a larger program of trying to take advantage of these assumptions, that these priors that we may associate with those variables. You see, most of the knowledge in our brain is not verbalizable, and some of it is. So that's the kind of division of System 1 and System 2 that I've been talking about in recent talks that this talk is also about. Now, there's the part of our knowledge which is verbalizable that we can reason and plan with, that we can communicate with language. And today I'll be telling you about that joint distribution between those concepts and how it can change in time in a way that may help us build better deep learning systems that can take advantage of these assumptions and priors. So this is really inspired by human cognition and the idea that machine learning really needs to put in inductive biases in order to gain generalization. in deep learning, we've already used a number of interesting inductive biases, but the kind of research I'm going to tell you about today is trying to add more inductive biases that are different from the ones we're already exploiting. And I have a list here of the kinds of inductive biases that this research is about. And in particular, in my talk, I'll be focusing on the red ones, which have to do with causality. So there's a notion that's very interesting in causality research of independent mechanisms, that the dependencies between these high-level semantic variables can be decomposed into small pieces corresponding to how different variables interact with each other and cause each other. And these mechanisms, which you can think of like the laws of physics, but at an abstract level, are what we would like to be able to represent. And many of these variables have to do with the things we name in language that have to do with causality often in some way. Agents, that could be the subjects, intentions and actions, which correspond to verbs, objects, which can be controlled. That often has to do with people or other agents doing things in the world and causing effects due to these actions. And one of the most exciting aspects of this point of view, so this is the third bullet, that thinking about it in terms of causality may help us deal with one of the biggest challenges in machine learning these days, which is how to generalize out of distribution, how to adapt quickly to changes in distribution. If you think about those changes in distribution in terms of interventions in the causal structure that explains how the world works, that actually gives us some answers about out-of-distribution generalization. So this will be at the heart of what I'll tell you about, and I'll talk about specific algorithms that are trying to take into account some of these assumptions. There are other aspects I won't talk about today, like the fact that these high-level semantic variables really correspond to thoughts and words and sentences, and so relating that abstract level of representation with natural language is also an important, useful thing we could add to put constraints on those representations. Another thing I won't talk about, but we have done work on, is how these mechanisms that relate these causal variables with each other, they're really generic. They could be applied to many instances, many objects of the same type, just like we do in programming with functions that can be applied to many different arguments that have a particular appropriate type. Another interesting area that we've been investigating, and that's connected to meta-learning, is the notion that a lot of that high-level knowledge is stable and has to do with the causal structure, while some aspects of it, which are due to interventions, can be changing quickly. And we would like to be able to take advantage of these different timescales and this notion of intervention and changes in distribution and how these changes occur. And finally, we also have work on how thinking about it in the way that humans solve problems and do credit assignment for learning can help us do it more efficiently. Okay, so first, the notion of systematic generalization is one way to think of how humans might be able to deal with out-of-distribution generalization by our ability to dynamically recombine existing concepts. And so this is connected with the idea that we have these relationships, these causal dependencies, but they can be applied and combined in new ways that allow us to deal with new objects we've never seen before, but that combine concepts we've seen already, even though these new ways may have zero probability under the training distribution. Humans are very good at that. But current deep learning is not very good at that, as we've seen in recent work. So one of the assumptions that is going to help us, I think, incorporate causality and generalize better out of distribution is to think about the structure of the joint distribution between these high-level semantic variables. And what I've been proposing for a few years is this idea that that structure is very sparse. So think of a sparse factor graph where the factors correspond to dependencies, those mechanisms. And what makes me think that they're sparse is to look at the way that we express knowledge with natural language, where something like a sentence is a statement that involves very few variables. So if I say, if I drop the ball, it will fall on the ground, it involves just, the ball, the ground, and the act of falling, and the position of the ball, right? So very few elements. And this kind of sparse dependencies are interesting and different from what we've been studying up to now in deep learning for the high-level variables, where we've generally assumed that they were marginally independent. I think this is too strong of an assumption. Instead, the kinds of concepts we manipulate, like ball and hand, have that sparse but still strong dependency structure that we need to take into account. So then the way to think about this is we have low-level sensory data like pixels and images, and we have these high-level semantic variables, and we have machinery like encoders and decoders that allow to map from one to the other. And so what we really want to do is to discover those high-level representations, as well as how to go from pixels to these semantic variables. So those variables are not necessarily given to us. And in addition to discovering the semantics of those variables as a function of the raw input, we want to figure out their causal relationship. So a lot of what I talk about is about discovering the causal relationships between a bunch of variables, in other words, discovering these causal graphs. One thing I won't talk about, but is also quite important, is where do actions come in all this? Actions correspond to changing things in that graph. You can think of them as special nodes that create interventions that change, for example, the value of a node. So one interesting aspect of this causal picture is that the interventions, the effective agents in the world, start with typically just one variable being changed. So in general, very few variables. So the change due to an intervention is going to be very much localized. Of course, then the effects of those changes could spread to many other variables. But the fact that the initial change is localized is something we can potentially exploit because those interventions, if they can be explained by very few bits in the model that have changed, that means that we can infer what the intervention was or how to take it into account with very little data. And so that means we can adapt to those changes very easily. Right? So, and that can give us a way to think of how, say, humans are able to do this fast transfer. If they have a good model of the world, then something happens, like I put on my dark glasses, that actually involves very few bits at the high level, just this one bit that says I put on my dark glasses, whereas there'd be many bits at the sensory level. Then there's a way for me to account for that change with very little data. In fact, a single example in that case, if I already have a fairly good model. And that means I can adapt to those changes more efficiently. But the argument we've made in a recent paper is you can take that story and turn it upside down and say, well, if having the good graph, the good dependency structure, and the good set of variables allows me to adapt quickly to a change when there is an intervention, then maybe we can go in the reverse direction. In other words, if I observe a change, if I observe a bunch of changes, the right kind of model should have the property that I can adapt quickly to those changes. And so that gives us a training objective, or at least some pressure on the right representations that we need to learn. So the kind of exercise we've worked on, and I want to describe it a bit more, regards discovering that causal structure from observational data where there is no change in distribution, no intervention, and from intervention data where there's a change in distribution. And although most work assumes that the intervention is known, that somebody tells you this particular variable has changed, we've been looking at the case where the agent observes that there's a change, but it doesn't know exactly which variable changed. And so you have to do inference over that change. So our first paper on this was published at the last ICLR and studies the case where you only have two causal variables and you have potentially two observed variables, x and y, which give you clues about the causal variables A and B. And so what you'd like to figure out in this very, very simple scenario is A the cause of B or B the cause of A, and what's the mapping between the AB couple and the XY couple? So in this work, we exploit only the speed of adaptation to the change in distribution due to an intervention on the cause, potentially the effect, but the one that really works well is on the cause, in order to learn what is the right structure of the causal graph. And the gist of how we can do that relies on the observation that you see in the figure that with the correct graphical model that A is the cause of B, the adaptation to an intervention where the x-axis here is the number of examples after the intervention, the adaptation to this sort of new distribution is going to be faster when you have the correct causal structure, A causes B, than if you have the incorrect one in gray, B causes A. So now we can use that speed of adaptation as an objective, as a meta-learning objective, to guide the discovery of the right causal structure. You can also use that same objective to figure out the mapping between the causal variables AB and the observed variables XY. In our case, it was a very simple setting where the mapping is a rotation, and the learner only had to discover the angle of rotation, which it does. The second work I want to tell you about has to do with larger graphs. So we try to scale up some of these same ideas in the context where the number of nodes in the graph might be 5, 10, 20, 50. And the algorithm we have explored has three phases. In the first phase, we're going to try to fit the conditionals in the causal graph based on the data, the observational data. We're gonna have a distribution over possible graphs, and we're going to sample graph structures according to that distribution. The way that the distribution is parameterized is with a single probability for each edge to be present or not, each directed edge to be present or not. And then when there is a change in distribution, we're going to see how the graph that we have sampled performs. We're going to then compute rewards according to this gradient estimator in the formula here that allow us to increase the probability of the graph structures that work well, and then we're going to refit the graph with those new, refit the causal model with those new probabilities. Now, we don't want to have a separate parameterization for each possible graph because there's an exponential number of graphs. And so the crucial trick here is to use the same parameterization for all the possible graphs. So the building blocks here are these conditional probabilities that calculate the probability of, say, one variable given potentially all the others. Then the graph structure is going to select which of the others are allowed to be direct parents. Now, we don't know what are the direct parents, but we have these probabilities for all of the edges that essentially tell us which variable should be a direct parent. And so we can sample from those probabilities. You can think of them as masks, like dropout masks. So when we train, we're going to be sampling those masks, but the same MLP with the same weights are going to be used across all the graph structures. This is what really allows us to solve the problem. So we've made a number of comparisons showing that this actually works quite well in many different kinds of graphs. The row M here is the size of the graph, and the first row here is the name of those graphs, so different structures. And then the other rows here correspond to other methods that have been applied. So we can see our proposed methods is doing quite well. a variation on this theme that we have explored to be able to scale to larger graphs is something that we find in practice, that you may have a graph that is partially known. For example, in biology, we would like to discover the causal graph that relates how different proteins or different genes or different drugs interact with each other. And we might know some of that graph, some of these edges, and then for the other edges, we really don't know. So this is the kind of problem that we're trying to solve, where we're trying to apply our learning technique on just the edges that we don't know, and somehow the fact that we're given already a subset of the graph, it turns out that really helps a lot to obtain good results. Yeah, the other thing I want to mention in these experiments is the use of machinery to propose the correct intervention. So I said at the beginning that we're not assuming that the interventions are known, and when we know what the intervention is, we can actually do something smart about which parameters are allowed to change. So if variable A is going to be intervened on, that means the variable is going to take its value according to the intervention mechanisms rather than the normal causal distribution. So it's like cutting the relationship between its normal parents and the variable and introducing a different parameterization for defining its distribution. Then during the period of the intervention, we really want to not change the regular parameters for that conditional. We only want to change the parameters for the other the variables that haven't been intervened on. Now, we don't know what the intervention is, but we use a simple heuristic, which is that the variable that is predicted in the worst way according to log likelihood is most likely to be the intervened variable. Now, in the future, one thing we want to do is to actually use a probabilistic inference on the intervention. But that heuristic already brought us a lot of good results, as I've shown here. So on this, thank you very much.
Hello, my name is Jan LeCun. I'm a professor at NYU and I'm chief AI scientist at Facebook. And today I'll be talking about energy-based models for self-supervised learning. So 2 years ago, I gave a talk at this same symposium and talked about self-supervised learning. And I'm going to go into a little bit more detail today about what this is. So I see three main challenges for AI and machine learning today. And the first one is to get machines to learn with fewer labels. It's pretty clear that humans and animals can learn how the world works, mostly by observation. And we don't seem to be able to reproduce this type of learning with our machines. We rely on supervised learning and reinforcement learning, but the type of learning that takes place in humans and animals seems to not require any supervision. The second challenge is learning to reason. Machines today in deep learning are able to solve problems by basically a fixed number of steps, the layers in the neural net. And the question is how to make reasoning, which involves a variable number of steps, compatible with deep learning, gradient-based learning, essentially. And then there is a third problem, which is learning to plan complex action sequences and learning to represent them. But I really don't have any good ideas about this. I'll talk mostly about number one, a little bit about number two. So how is it that humans and animals can learn so quickly? Babies learn basic concepts about the world, mostly by observation at various times in their lives, but they accumulate an enormous amount of background knowledge about how the world works in the first few months of life. And perhaps this is the source of what we call common sense. So things like learning about gravity, learning that an object that is not supported will fall, happens around 9 months of age. And intuitive physics, takes about that long. What type of learning principles do humans and animals use to be able to learn this kind of thing? So the hypothesis that I've been formulating for a number of years is that perhaps this type of learning is what I call self-supervised learning, which is really a form of unsupervised learning. And the idea is to capture dependencies between variables by predicting a subset of variables from every other subset of variable. So let's say that we have a video that we're trying to predict the future of, right? So we are shown a few frames of a video, and we ask the machine to predict the next frames of the video. There are many things that can happen in the future, and the problem is how to represent the uncertainty and the set of all possible futures that could possibly happen. But that's a form of self-supervised learning. Self-supervised learning does not necessarily mean predicting the future. It might mean predicting the past from the present. It might mean filling in the blanks wherever that occurs. But this idea of learning by prediction is very rich because there is a huge amount of information in the data that can be used, and we don't need to manually label this data. The two things that self-supervised learning can be used for, the first one, of course, is to learn representations of the world, hierarchical representations of the world, so that those representations can be used in subsequent steps to learn a particular task in supervised or reinforced mode. The second one is to learn predictive forward models of the world, which would allow a system that can produce actions to plan ahead what kind of actions to take so that a particular result will ensue. But the main question here, the main technical problem we have to solve is how to represent uncertainty and multimodality in the prediction. And for this, I'm proposing to use energy-based models. I alluded to this about 2 years ago when I gave a talk in this forum. But let me go into a little bit more detail. So an energy function, an energy-based model, is really an energy function, which is a scalar-valued function, f of x, y. X is an observed variable, and y is a variable to be predicted. And the system does not produce a y variable. It just tells you whether, when you give it an x and a y, whether those two are compatible with each other. So let's say x is an initial segment of a video. If y is a good continuation of that video, then f of x, y will take low values. And on the contrary, if y is not a good continuation of the video x, then f of x, y will take large values. This is symbolized at the bottom here in 2 dimensions, where x is a scalar value, y another scalar value, and the blue beads represents the data points. Those two energy functions here, depicted here, essentially give low energy to good samples that come from the data and higher energies to everything else. This is what's necessary when you want to use an inference algorithm that produces a good prediction y by minimizing this energy function f of x, y. So let's look at this diagram here where the data points are represented by those black dots, and the energy function here, I'm depicting the lines of equal cost of this energy, equal height if you want. So the inference process would consist of starting from a point and then kind of finding a nearby point in the space that has low energy, perhaps for a fixed value of x, or perhaps not. So this is inference. We've not talked about learning yet, but how do we train an energy-based model? There are two classes of methods. There are contrastive methods, first of all, the C+1, and regularized architectural methods, which I'll talk about later. So contrastive methods consist in showing a data sample, a blue bead in this example, pushing down on its energy, so you can compute the gradient of the energy function with respect to its parameters, and you can decrease the corresponding energy. But then you also need to make sure that the energy outside of the data manifold is higher than on the data. So you pick a point, in some ways, outside the data manifold, and you push its energy up. Those are called contrastive learning, obviously, because you have those two terms, one pushing down, one pushing up. The trick is how you find those contrastive samples whose energy you're going to push up. And that's where contrastive methods become inefficient, because in a high-dimensional space, it's very difficult to push on all possible ways that a point can be outside a data manifold. So I put together this chart, which I'm not expecting you to read fully today, but for reference, most of the algorithms, learning procedures for unsupervised learning that we know belong to one of those two categories, contrastive or regularized. So things like maximum likelihood is contrastive, metric learning Siamese networks is contrastive, generative adversarial networks are contrastive, masked autoencoders are contrastive. And then regularized architectural methods are methods like sparse coding, sparse autoencoders, and variational autoencoders. So let me start with denoising autoencoders, because it's become very popular in recent years for natural language processing, for sort of pre-training natural language processing systems in a self-supervised manner. Denoising autoencoder actually originated in Pascal Vincent's publication in 2008. I had worked on this before in my PhD, but in a more restricted case. And recently, it's become extremely popular for training so-called transformer architectures to represent text in a self-supervised manner. So you take a piece of text, Y, you corrupt it in some way. And the way you corrupt a piece of text is by, for example, removing words from it or replacing words by kind of a blank marker. And then you train a neural net, a transformer architecture in this case, to basically predict the words that are missing. In the process of doing so, the system learns good representations of text because it has to be able to predict whether the word that is missing is cat or dog or a car or a table or a verb of some kind. So it needs to essentially understand the role of words in a text, but also the semantics. So this type of pre-training has become incredibly successful and has become in a very short time essentially the standard method for pre-training natural language processing system, and has really revolutionized NLP, as many of you probably know. So there's a key paper by Wazwani from Google presenting the transformer architecture, followed by the BERT model, which used this sort of self-supervised learning. Now, those things work really well, and you can train transformers to represent text and then use the internal representation as input to a subsequent system that does text classification or, let's say, translation. This is an example from two of my colleagues at Facebook Research in Paris who have trained a transformer to basically represent multilingual text. So half of the text is, let's say, in English, the other text in Korean, and you remove random words, and the system learns to use the text in one language to predict the words in another language. In the process of doing so, learns a language-independent representation of text, which you can then use as the basis of a translation system. Another work also by Guillaume Lample and another collaborator, François Charton, also from Facebook in Paris, has used transformers to learn to solve equations like computing an integral or solve a differential equation symbolically, which is really astonishing. And there's been other work at Facebook in dialogue systems. So this is a dialogue where a machine and a person can look at a picture and they comment on that picture and ask themselves questions. It's a little hard to figure out who is the machine and who is the person in this dialogue. The machine is actually in gray and the person in blue. Those dialogues are quite big progress compared to what was possible a few years ago. This work is more recent. This is from Nicolas Carion, who was a resident PhD student at Facebook until recently and is now a postdoc at NYU working with me. And he built a system that uses a convolutional net as a front end and a transformer as a back end to do end-to-end object recognition, detection, and localization. I think this is the future. So I think a lot of future vision systems will actually use a combination of convolutional nets and transformers or other ways of doing object-based inference. And this system is really interesting and works very, very well for sort of dense semantic instance segmentation and what's called panoptic semantic segmentation, which includes labeling every pixel of an image with the label of the object it belongs to. So people, of course, had the idea of using denoising autoencoders in the continuous case, for example, to learn features for images. You take an image, you blank out some parts of the image, and you train the system to recover the missing parts. Those systems do a pretty good job at reconstructing the image, but the features that are learned by those systems are not very good. If you use them as inputs to a subsequent image recognition system, they don't give you very good results. So it's been largely a failure. But what's been much more successful over the last year or so is so-called contrastive embedding method. So the idea goes a long time. I had a paper in 1993 on this topic and more in 2005, 2006, but it's been sort of made very popular in the last year or so with methods such as Pearl and Moco, which came from Facebook, and SimClear, which came from Google. And the idea is you have two identical copies of the same neural net, convolutional net in this case for images. You show two images that are basically just transformations of each other. So they have the same content, and you force the system to basically produce the same outputs. You have a cost function that says the two outputs should be identical or very close to each other. And then you show a contrastive pair. Two images are different, and then you tell the system the energy, which is the distance between the two vectors, should be large. Okay, so it's one of those contrastive methods where you push down on the energy of good samples and push up on the energy of bad samples. The problem with those methods is that they require a very, very large number of training samples, particularly negative training samples, and they require to use what's called hard negative mining to kind of choose the negative samples appropriately. But they do work, and they produce visual features that are somewhat useful. The cost functions that can be used for this all have the same characteristics, that they take the energy of the correct answer and try to push it down, and the energy of some sort of incorrect y, if you want, called a y hat here, and try to push it up. And there's different ways of doing this, which I'm not going to go into the details of. But this is a slide that just kind of shows that maximum likelihood, when you kind of come down to it, is a type of contrastive learning that unfortunately very often runs into intractable integrals, and so you have to make approximations. The type of loss functions that are very popular for contrastive embeddings is called NCE, noise contrastive estimation, and it consists in taking a batch of samples with some positive, some negative, and then feeding their scores, their energies, into kind of a softmax that pushes the energy of the negative sample, the contrastive samples, to large values, and then pulls the good ones to small values. Now, over the last few months, there's been a couple of methods that have been proposed that don't actually require contrastive samples. And an interesting one is called BYOL, Bootstrap Your Own Latent, that came out of DeepMind. And the idea there is that you slow down the evolution of the weight of one of the two networks, so they don't have exactly the same weights anymore. And you stick a predictor on top of one of the two networks. And for some reason, this works. It's not fully explained. It's not fully understood, even by the authors. There's some theoretical work on this to try to understand why this works. But it does work, and it produces features that actually rival the type of features you would obtain by training purely supervised on ImageNet. Another method proposed by Mathilde Caron from Facebook in Paris, called Deep Cluster and SWAV, use a sort of different idea, but also do not require kind of contrastive phase. So those are the two top performing systems to learn self-supervised visual features, and the performance they produce is essentially the same as what you would get by training purely supervised. Okay, so now let me talk about architectural and non-contrastive methods. And the basic idea of those methods is to limit the volume of space that can take low energy in some ways. And a good example of this is the well-known k-means algorithm, right? So k-means is a procedure that basically captures the dependency between the individual variables of a vector y that you'd like to model the distribution of. And there is a latent variable z. This latent variable is multiplied by a prototype matrix, and the reconstruction is just a product of the z vector by the prototype matrix w. The z vector is constrained to be a one-hot vector, so it's a vector with all zeros and 1, 1. And the way you compute the energy function, f of y, is that you take an energy function e of y z, which is a reconstruction error for a particular z, and you find the z that minimizes this reconstruction error. So you find the prototype, the column of w, that is closest to the prototype y. And if you train k-means, this is a depiction here of the energy surface of k-means when you train with samples that are drawn from this ellipse data manifold here. What you get is prototypes that are equally spaced along this manifold, and you get sort of energy wells around each of those prototypes, and the overall energy is just a minimum of all of those energy wells. So a kind of a dark spot here is a minimum of the energy, and the bright spot are more like ridges or maxima. So this seems to work pretty well, but it doesn't work in high dimension. K-means is not really particularly good in high dimension. It's an example of what's called a latent variable model, where you're given observations X, and during training a desired Y, and what the system has to do is find a value of Z, the latent variable that minimizes this energy, and you define the new energy as the minimum over Z of E of XYZ, which is a more elementary energy function. The reason for using latent variable models is that it allows to make predictions in a multimodal way. So if you want to do video prediction, for example, there are several future video frames that are possible that follow an initial segment. And so you start from a variable X, and you'd like to be able to parameterize the set of possible predictions of Y bar, which is depicted by this sort of S-shaped ribbon here. And what you can do is have a latent variable that can vary within a set, and as you vary the latent variable within a set, the prediction varies over this this ribbon, this sort of data manifold. Again, inference consists in, given an X and a Y, finding the Z that minimizes the energy, the C of YY bar, the discrepancy between the prediction and the observation. But in inference mode, once you've trained the system, you don't have Y, of course. So to deal with those latent variable models, there are kind of two types of methods. The methods that by construction limit the volume of space that can take low energy, like K-means, and then other methods where there is a regularizer that limits the volume of white space that can take low energy. And things like sparse coding, sparse autoencoders, and variational autoencoders belong to this category. So in general terms, a self-supervised learning system of this type would take a variable X, run it through a predictor, extract a representation from it, and then feed a latent variable Z to a decoder. The latent variable would parameterize the set of possible predictions, and the possible predictions are the Y bars. To limit the volume of space that can be predicted by swapping Z over a set, you add a regularizer, which is a term in the energy that makes the system pay whenever Z goes outside of a particular domain. And that regularizer essentially makes the system automatically give higher energy to data points or region of space you don't train it on. There are various ways to regularize this way. You can discretize Z, you can minimize an L0 norm or L1 norm, or add noise to it, which is what variational autoencoders do. This is an example of a well-known algorithm called sparse modeling or sparse coding, where what you see here is a depiction of the columns of a W matrix that is multiplied by a latent vector Z, and the animation shows those filters or prototypes being learned or trained on natural image patches. So they naturally develop oriented edge detectors. And this is a well-known algorithm that is from the late 90s from Olshausen and Field. Now, the problem with this kind of decoding architecture is that you have to infer Z by minimizing a cost function. And it's much more efficient to be able to predict this, the value of this variable through an encoder. So this is essentially a regularized autoencoder, where R of Z could, for example, be a L1 norm, which would make the Z sparse. So this is called using an encoder training an encoder to predict the optimal value of a latent variable that would otherwise have to be obtained through optimization is called amortized inference. My former postdoc, Carol Greger, and I had a paper about this at ICML. And this works really well for things like learning convolutional filters and things of that type. And this is another example here where the filters that are learned here are learned on CFAR 10. They're convolutional codes, and you get very sparse representations for a particular image here. Now, variational autoencoders are a very popular method, and they can be interpreted in the context of energy-based models. And I'm going to go into the details of it, but the basic idea of how variational autoencoders limit the information content of the code is that they limit the norm of the code, and at the same time, they make the code vectors noisy, which basically limits the number of noisy spheres that you can pack in larger sphere of minimum radius. And that's how rational autoencoders, the kind of mechanical analogy, if you want, sort of minimize the capacity, the information capacity of the latent variable. I'm going to conclude by showing an example. I showed an early version of this 2 years ago of using conditional regularized latent variable energy-based models, in this case, a variation of rational autoencoder with amortized inference, to do video prediction to help with tasks like autonomous driving. So here we have an X, which is an initial segment of a video, goes to a predictor, and then the representation goes into a decoder, which, with the help of a latent variable, produces a prediction. The latent variable itself is regularized and can be, the inference of it can be amortized by training an encoder to do the right prediction. This application here that is shown is for predicting, it's for helping with autonomous driving. So we are in the blue car in the center of this image, and which is kind of a top-down view of a highway, if you will. And the system is supposed to predict what the cars around itself are going to do in the future, and that may help with planning a good strategy. This is an example of the system running where the latent variable is drawn from differently for the 4 columns on the right, and you see different futures being predicted by that system due to different drawings of the latent variable. If you don't have a latent variable, you get the second column from the left, where the predictions are very blurry because the system cannot make sort of multimodal prediction, it has to make one, and so it predicts the average. Now, why are those predictive models interesting? It's because if you have a predictive model that predicts what cars around you are going to do, or predicts what the world is going to do more generally, you can use this together with an objective function to infer, using optimal control, infer a sequence of action that will arrive at a particular result using gradient descent. It's very simple. That has been known since the 60s by control theorists. So you can do that, but you can do also is by gradient descent, you can train a neural net, P of S here, a policy network, to actually predict what the best action would be at any one time to minimize the overall cost predicted over a segment of time. And this is how you can train a car to drive itself on the highway safely, essentially, by using this kind of method. Okay, I'm going to conclude. So putting this all together, if we want to build autonomous intelligence systems, we're going to have those. We're going to need those systems to have hardwired, built-in trainable models of the world. They can predict future states, and that's going to use self-supervised learning. We're going to need critics. So critics are modules that predict the expected value of an objective in advance. We're going to need actors. So actors are like those policy networks. They given an objective and a model of the world, what is the best action I can take now to kind of minimize the objective? And the cost function is sort of instantaneous. The critic kind of predicts the future values of the cost. So there is a hypothesis here, which is a little crazy, that I've been making, which is that in the human brain and in most animal brains, there is only one model of the world. There's basically one piece in your prefrontal cortex that we can configure to model the situation at hand. But it's a single engine, if you want. And perhaps this is what attention really means. Attention of the attention of we can only do one thing at a time, essentially. And it's because we have to focus our attention on a particular problem, but we configure our model of the world for the situation at hand, and we cannot use it for anything else at the same time. So this may be a limitation, in fact, of our system. Okay, I'll conclude with a couple of conjectures. I think self-supervised learning is really the future of AI. We certainly see it with natural language processing. I think it's coming for computer vision and robotics and a number of other applications, speech recognition and things like that, multimodal systems. Models of the world are necessary, so machines will need to learn how the world works around them through SSL. Perhaps this is the type of learning from which common sense might emerge from machines if we manage to make this work properly. Reasoning is finding actions that optimize outcomes, that kind of satisfy constraints, minimize costs, and so I think we can view reasoning in the context of energy-based models as just energy minimization, essentially. And perhaps a crazy hypothesis is that consciousness is the deliberate configuration of a world model, so that it views solves the situation at hand. I'd like to conclude by saying that there is no such thing as artificial general intelligence, although the phrase is very popular currently within the field. Intelligence is always specialized. Human intelligence is very specialized. And so I don't think we should talk about general intelligence. We should talk about human level intelligence. So perhaps before that, rat level or cat level intelligence. And perhaps we'll see this in the context of a lifetime. Thank you very much.
Hi everyone, my name is Chelsea Finn. I'm an assistant professor at Stanford University. I'm sorry that we couldn't be together in person today, but I hope that we'll have an opportunity to meet each other in person at some point. Today I'll be talking about meta-learning from few-shot adaptation to uncovering symmetries. The core motivation of what I'll be talking about today is a gap between our current paradigm and our current reality. At least in machine learning research, our current paradigm is to take a training data set, train a model on this data set, and then ultimately evaluate this model as is, as a static model. In contrast, our current reality is that the world is constantly changing, from stocks to changes in supply and demand over time to robots entering different parts of the world throughout the course of their lifetime. So what I'd like to talk about today is whether our algorithms can handle the changing world rather than just simply deploying a single static model. Now, you might be wondering, how does industry cope with such a changing world when we develop our algorithms to produce static models? Well, if you ask Chip Huyen, who works on machine learning in production, she would say that machine learning systems degrade quickly because of concept drift. And for online machine learning systems, you want to update them as fast as humanly possible. So clearly, the way that our techniques are being used is not the way that we intend when we develop machine learning algorithms in research. And if we have a mechanism to bridge this gap, to actually prepare models for this constant change in the data distribution, perhaps we would be able to have a much broader impact. One approach to solving this problem is to use fine-tuning. And fine-tuning works very well. From computer vision to natural language processing, we've seen large gains in accuracy, for example, when you pre-train on ImageNet, and large improvements in error rate when you pre-train on language modeling and fine-tune on other downstream data sets. More recently in robotics, we've also found that the same trend holds. If we pre-train a robotic grasping system with reinforcement learning and then fine-tune it on drastically different situations, including harsh lighting, transparent bottles, a checkerboard background, and even a change in the robot's morphology, we see substantial gains when we use fine-tuning. The downside, though, is that fine-tuning also has its limits. It requires a non-trivial amount of labeled data in order to adapt to these new circumstances. So what I'd like to talk about today is how we can start to bridge this gap. Can we introduce assumptions that allow us to generalize further with less data? And can we make these assumptions as mild and broadly applicable as possible, yet also powerful in what they enable? A core aspect of what I'll talk about is meta-learning. So with this in mind, my talk will have three parts. First, I'll give a brief overview of meta-learning and what it's currently capable of. I'll also talk about whether we can use meta-learning to capture equivariances, to allow us to generalize further. And finally, I'll talk about whether we can fine-tune to distribution shift without any labeled target data. But first, let's talk about what meta-learning actually is. And to do that, it's helpful to look at an example. In particular, let's look at a few-shot image classification example. The goal here is, given one example of 5 different classes, essentially a little tiny training data set, can we classify new examples as being among one of those 5 classes? Unfortunately, if you train from scratch, or even if you fine-tuned on this data set, your model would probably overfit heavily to such a small training data set. So what meta-learning algorithms aim to do is they aim to essentially learn how to learn other tasks in order to prepare the model to perform this few-shot classification task. So for example, what we can do is we can take image data from other image classes and structure it into mini training data sets and test sets. With this data, with these training classes, we can train a model how to learn from small amounts of data. And then after learning how to learn or meta-learning across these tasks, at meta test time, when given held out test classes, when giving a training data set from a held out test classes for this new task, it can effectively generalize to the new examples. Of course, this is an example specific to image classification, but you could also replace this example with problems like regression, language generation, skill learning, and really any machine learning problem. Now, this is how the problem setup looks like. How do meta-learning algorithms actually solve this problem? One approach is to parameterize the inner learning process using a neural network itself. So you can take the training data set and pass that data into a neural network model and train the model to essentially learn from that data such that when it's given a new example, it can effectively predict the correct label and generalize to that test example. So this is one approach. Another approach to bring a bit more structure into this inner learning process is to embed an optimization inside the learning process. So instead of parameterizing the neural network, parameterizing the learning process as a neural network, we can parameterize it as an optimization process with some trainable parameters. So for example, we may have an initial neural network. We can run gradient descent on our tiny little training data set to get another neural network and train this entire process such that when we give it a new example, it can generalize effectively to this example and predict the correct label. Different algorithms correspond to optimizing different parts of this optimization process and optimizing them in different ways. The model-agnostic meta-learning algorithm optimizes for the set of initial parameters of this learning process such that one or a few steps of gradient descent produce a model that generalizes effectively from that tiny training data set. So that's how meta-learning works. What are these algorithms capable of? One thing that we showed recently that you can do with these algorithms is allow them to enable robots to adapt to new objects that they haven't seen before. For example, you can show the robot something that you want to do, like placing a peach into a bowl. It can adapt its weights to this task and to this object such that it gets a policy that can drop the peach into the bowl for different positions of the bowl. Beyond this one-shot imitation learning problem, meta-learning has also been successful at adapting to new molecules that it's never seen before, with potential applications to low-resource drug discovery. It can also be used to allow robots to adapt to new terrains and conditions that they experience over time. And finally, it's also recently been used to enable models to be adapted to new regions of the world for predicting the land cover segmentation of an image. So here are a wide range of applications of meta-learning that allow you to very quickly adapt a model to something that has changed about the world. Now what I'd like to talk about next is how we might go a bit further. So next I'll talk about capturing equivariances. And the motivation for this part is that there is actually a second solution to handling distribution shift, which is to try to build in structure into the model that captures the kinds of shifts that you'll see at test time. So for example, you can build in translational equivariance into a neural network using convolutions. And this will allow the model to generalize more effectively to data that has been translated. This is great when we know the structure and how to build it in, but unfortunately, oftentimes we don't know that, and this isn't a viable solution in those cases. So with this motivation, we wanted to see whether we could discover equivariant and invariant structure among a set of tasks using meta-learning, then build in that structure such that we can generalize effectively when given new data sets. So how do we go about doing this? One thing that we can do to think about this problem is thinking about how equivariances are represented in neural networks. And first, let's look at an example, specifically the example of convolutions. So here's an example of what a convolution layer looks like, where you slide a filter across an input X to produce an output Y. it turns out that you can represent this same convolution using a fully connected layer, where the weights of the filter are repeated across the matrix. They're essentially shared in different parts of the matrix, and the rest of the matrix is 0. Now, with this example, what we're going to try to do is reparameterize this weight matrix to separate how equivariances are learned from the underlying filter parameters. So keeping along the example of convolutions, what we can do is we can reparameterize this weight matrix W into first the underlying filter parameters A, B, and C, and how these filter parameters are shared and copied within the weight matrix. And if you take the matrix vector multiplication of these two things, we get a flattened version of the weight matrix on the left. We'll refer to this matrix and vector as U and V, and essentially U can capture the symmetries, how parameters are shared, and V can capture the underlying shared parameters. It turns out that we can prove that theoretically this U and V can directly represent a decoupled equivariant sharing pattern and filter parameters. And it can directly represent this not just for 1D convolutions, for example, but for all group convolutions with finite group G. This covers things other than convolutions like permutation equivariance and some forms of rotation equivariance. Okay, so now that we have a mechanism to separate out the equivariance from the underlying parameters, now we have a way to actually meta-learn equivariances that allow us to translate those equivariances to new tasks. In particular, what we'll do is in the inner loop, we'll only update the underlying parameters, keeping the equivariance fixed. And in the outer loop, we'll learn the equivariance U and the initial parameters. So essentially what we're doing here is training the model such that when you have these equivariances fixed and you update the underlying parameters, you'll get a model that generalizes well. And this will allow you, in situations where you have symmetries shared by a range of tasks, to potentially uncover these symmetries and keep these symmetries fixed when you're learning new tasks. We refer to this method as meta-learning symmetries by reparameterization, in the sense that we're reparameterizing the weight matrices in the network and keeping part of that matrix fixed and part of that matrix learned in the inner loop. Now, experimentally, we wanted to understand whether we could recover convolutions from translationally equivariant data. To study this question, we generated a number of synthetic tasks where each task corresponded to a different translationally equivariant function, and we had small data sets for each of the tasks. And from this synthetic data experiment, we found that MSR built on top of fully connected networks is able to perform just as well as MAML when you're using convolutional layers. And it's also able to significantly outperform MAML with fully connected layers and locally connected layers, indicating that it's able to recover something that is as capable as the convolutional inductive bias. Okay, and further, we can actually show that with MSR, we recover a weight matrix that looks like this, that exactly corresponds to a fully connected representation of a convolution, where we have exactly the A, B, and C parameters copied across the diagonal of the matrix. Further, we wanted to ask whether we can recover something better than convolutions. To do this, we looked at first data with partial translation symmetry. So we took some locally connected functions with varying numbers of underlying filters, either one filter, which directly corresponds to convolutions, or 2 and 5 filters, which had only partial translation symmetry. And we find that in these cases, MSR is able to perform significantly better than MAML with convolutions because it's able to recover the correct symmetry underlying the data. Further, if you have data with translation, rotation, and reflection symmetry, MSR is also able to recover the underlying symmetries, in this case, rotation and reflection, when you build in translational symmetry, and perform significantly better than convolutions, which isn't able to capture the rotation and reflection symmetries. Great. Now, beyond these synthetic experiments, we wanted to understand whether we could learn from augmented real data. To do this, we we constructed a meta training process that looks like this, where we wanted to try to bake data augmentation into the architecture or update rule of the network. So in this case, we took the training set and the validation set for each task, and we augmented the validation set with different transformations of the data, and essentially trained a model such that when it adapts with an unaugmented training data set, it can generalize much further to augmented data. In this setting, we found that MSR is able to significantly outperform mammal and other variants across the board, and also perform comparably to prototypical networks when tested on OmniGlot, and significantly better when tested on the more difficult mini-ImageNet problem setting. Okay, so kind of the takeaway from that part is that we're able to, by actually kind of recovering and encoding symmetries inside the neural network, we're able to generalize further, potentially, using this particular form of meta learning. However, we still need label data in this case in order to adapt. So what I'd like to talk about next is if we can fine-tune an adaptive distribution shift without any labeled target data. We'll specifically consider, in this case, a form of distribution shift called group shift. And what I mean by that is we'll have a categorical group variable Z. This may correspond to the user, the location, the time of day, and can be easily derived from metadata. And we'll assume that our training data comes from this distribution and our test data comes from this distribution, where the distribution shift is captured by this underlying variable Z. This can capture things like label shift and most forms of covariate shift, and it can also capture realistic problem settings like federated learning. Now, how do we go about solving this problem? So previous approaches for tackling this form of distribution shift have built upon the idea of distributionally robust optimization. And the way that these algorithms work is they form an adversarial distribution Q of Z, and they optimize for the worst case distribution over this variable. So for example, the worst case group. These approaches can enable robust solutions that are robust to the distribution shift, and they're less pessimistic than adversarial robustness techniques because they're optimizing over a smaller set of perturbations to the data distribution. But they often sacrifice average or empirical group performance as a result of optimizing for the worst case distribution. So we want to be able to overcome this limitation by adapting for distribution shift rather than trying to be robust to distribution shift. In particular, we'll assume that we have unlabeled data from the test subdistribution. So for example, we'll have new unlabeled data from a new user, a different time of day, or a new place. In the case of federated handwriting recognition, we might have unlabeled data that looks like this. And then we want to be able to use this data to adapt our model and infer the labels of these data points. And the assumption here is that the test inputs from one group, from one user, one time of day, and so forth, are available in batch or in a streaming setting at test time. We think that this is a fairly realistic assumption since oftentimes data is arriving from a single time of day or a single place at test time. We refer to this kind of general problem setting as adaptive risk minimization in the sense that at test time, we're given the opportunity to adapt our model. What the training procedure looks like specifically is we construct different subdistributions of the training data using our groups, and then we train for adaptation to each of these subdistributions. And in particular, this adaptation process, like I mentioned, will use unlabeled data. And we can experiment with a couple different meta-learning approaches to allow this fast adaptation to unlabeled data. This includes the model-agnostic meta-learning approach using a learned loss function, where we're running gradient descent on the unlabeled data using this learned loss. The second approach that we'll consider is meta-learning with a context variable, where we have a neural network that takes as input the unlabeled examples, produces a context, and uses that context when making predictions for the test example. In the simplest setting, this context variable can simply correspond to the batch norm statistics, where critically what we'll be doing is training the model such that when it's given data, unlabeled data in a group, it can use the batch norm statistics to adapt to that part of the distribution. Now, how does this work in practice? So on the federated extended MNIST dataset, we compared to a number of different approaches. We compared to empirical risk minimization, or standard neural network training. We compared to distributional robustness, like I mentioned before, and also a baseline that upweights the groups to the uniform distribution rather than being skewed. And when we try to adapt to a new user using unlabeled data, we find that we're able to perform significantly better than these methods. So we compared to these methods, we also compared to a federated learning method, and the results are here. We see a 5% improvement in average accuracy, average across the users, and we see a 10% improvement in the worst case scenario, in a scenario where, on the worst user, essentially. And this evaluation is important because oftentimes you don't want your service or your network to work great for some people and work terribly for other people. We also evaluated on the CFAR-C and Tiny ImageNet-C datasets, and we were, in this case, adapting to new image corruptions. And we trained using 56 corruptions and tested using 22 disjoint or held out corruptions. And again, we find in this case that we see large improvements both in average accuracy and worst case accuracy, with an 8% improvement in worst case Tiny ImageNet-C performance and a 21% improvement in worst case CFAR-10C accuracy in the worst case. Okay, so to wrap up, if you take away nothing else from my talk, it's that there's this gap between our current paradigm and our current reality. In machine learning research, we often assume that we're going to be evaluating a static model, while in reality, the world is constantly changing. I talked about 3 approaches for trying to bridge this gap, starting with the general framework of meta-learning for enabling very quick adaptation to changes in the world. I then talked about preliminary evidence of meta-learning being able to capture equivariances in the data via reparameterized weight matrices. And I finally talked about how we can fine-tune and adapt to distribution shift with only unlabeled data. With that, I'd like to thank my students, especially my students and collaborators who did a lot of the work that I presented today, including Alan, Tom, Marvin, Henrik, Nikita, and Sergey. If you're interested in learning more, all of the lecture videos for my course on meta-learning are available online, and I look forward to your questions. Thank you.
Thank you, Dr. Benjio, Dr. Lukun, and Dr. Finn. Now, Dr. Sung-Woo Hwang, the president of SAIT and the co-chair of this forum, will give us a speech.
Good morning, afternoon, evening, everyone. Thank you very much for all your participation in Samsung AI Forum this year again. All the members of Samsung have great intention to make this forum more interesting and meaningful for both academia and technical world. Therefore, we have taken 2 important steps this year. The first step is asking Professor Benjio to become an official chair of a forum with the title of Samsung AI Professor. He kindly accepted it. The second step was selecting Samsung AI Researcher of the Year. The purpose of this is, of course, to promote all the young researchers in this field. We have taken more than 100 talented applications from all over the world. I am sorry to tell you that we had to take only just a few of them this year, but don't worry, you are all great, and this is my responsibility as a co-chair to continue this program. Now, I'm going to ask Young-Sang Choi to announce all the selected people this year. Thank you.
Thank you, President Hwang. As Dr. Hwang introduced, we have established the Samsung AI Researcher of the Year to encourage young AI researchers under the age of 35. From a large pool of excellent applications, we have chosen 5 awardees by a thorough evaluation process from the reviewers of renowned professors and inside experts of Samsung. I would like to give my sincere gratitude to all applicants. Now it's time to find out who the awardees are. First, Dr. Byung-chul, Dr. Chelsea Finn, Dr. Seth Fluxman, Dr. Jiajun Wu, Dr. Zhuori Xie. Congratulations again. On the forum website, you can check out the contributed talks of these awardees. Now, let's move on to Dr. Yoshua Benjo, a co-chair of this AI forum. We'll have a time to explain why we chose these amazing researchers as the Samsung AI Researcher of the Year. Now, let's meet Dr. Benjo on the screen again.
Hello, it gives me great pleasure to tell you today about the winners of the Samsung AI Researcher of the Year awards. So the 5 winners are Byung-chul, Chelsea Finn, Seth Flaxman, Jiajun Wu, and Cho Ju-si. Let me say a few words about them. These people are young researchers who have made remarkable impact in the field of AI. For example, Byung-chul has made amazing impact in natural language processing. Chelsea Finn has made incredible impact in meta learning and robotics with reinforcement learning. Seth Flaxman has been very influential in his work on, for example, COVID-19. Jiajun Wu has been making incredible work at the intersection of computer vision, machine learning, and cognitive science. And Cho Ju-si has won many awards already with his focus on computational efficiency and robustness. So it was really a pleasure for my colleagues to look at their work in the last few years and choose them for this very, very nice prize. I'm very proud of them. And I thank Samsung for having created this prize and giving it to these amazing young people. Thank you.
Thank you again, Dr. Benjo. Congratulations to the 5 Samsung AI Researchers of the Year 2020. I wish you have an even bigger contribution to the world from now. We have the awardees connected. Now let's listen to their voice. Dr. Byung-chul, are you connected?
Let's see.
Yeah.
Yep, hopefully now you can hear me. Yep. Thanks for the award, and it is my honor to receive them together with the fascinating other awardees, 4 of them here. And I'm going to take this as an encouragement from Samsung to continue on my research. And I hope to actually have more collaboration with the people from Samsung as well as the people all over the world. Thank you very much again.
Thank you. Dr. Chelsea Finn.
Thank you for the award. I'm honored and humbled first to have been invited to speak at the forum after Yoshua and Jan, and also to have been selected as one of the awardees, especially alongside these 4 amazing researchers. I'd also like to thank my incredible students and collaborators and thank Samsung for the recognition. And it'd also be great to continue doing work in these areas and potentially collaborate with the other awardees as well.
Thank you. Dr. Seth Fluxman.
Hi, thank you. I'm really honored to receive this award, to be in the company of these leading AI researchers. I want to thank all of my collaborators, colleagues, students at Imperial College London, especially the team I've been working with on the COVID-19 research, the Imperial College COVID-19 response team. Thank you to the panelists and the organizers at Samsung for the recognition.
Thank you. Dr. Jiajun Woo.
Thanks for, I feel very honored to have received the award. Very excited to be in this place with other awardees and listening to these fascinating talks. And hoping in the future that we can have more collaborations. I'm already collaborating with Chelsea on some research project. Hopefully we can have more in the future with other awardees and also with Samsung researchers. Thank you.
Thank you. And Dr. Chu Rui Xie.
Yeah, thank you. I'm very honored to receive this award, and thank you for Samsung for the recognition, and also this very nice committee, and also I'm looking forward to the collaboration with other awardees and Samsung AI research. Thank you.
Thank you, all of you, and congratulations again. As I said before, on the forum website, you can check out the contributed talks of these awardees. Now, let's move on to the next session. This presentation session has 3 talks from speakers from industry. First, Dr. Don-hee Ham of Samsung and Harvard University will give a talk on the reconstruction of the brain. Second, Dr. Tara Sinath from Google Research will present on towards end-to-end models for speech recognition. Lastly, Dr. Jen Wortman-Vaughan from Microsoft Research will talk about the intelligibility throughout the machine learning life cycle. Following the talks, we will have a live discussion panel and Q&A session. Please keep connected with us. And now the session begins.
Hi, everyone. I'm Tara Sinath. I'm a research scientist in the Google Speech team. And today I'm going to talk to you about a joint effort between the Google Brain and Speech team regarding end-to-end speech recognition advances that the team has made over the past few years. So before I begin, let me explain a little bit what we mean by end-to-end ASR. In a conventional system, we have an acoustic, a language, and pronunciation model to map our acoustic features all the way to words. Each of these modules is separately trained and independently optimized. As an alternative, when we say end-to-end, we want to take acoustic features and map them directly to words with one neural network. Another issue with current conventional model approaches is that each of those submodules is trained to optimize a different criterion. And when we mean end-to-end, we mean that our neural network is optimized for the metric that we care about in speech recognition, which is word error rate. So to give a more pictorial representation, the top picture shows a conventional model, where we take a set of features and an acoustic model maps these features to a set of subword units, for example, phonemes. We then have a pronunciation model, which maps phonemes to words, and a language model, which will give us a probability of words following other words. This is then followed by a potential second pass or score before we output the final hypothesis. Each of these modules is independently trained and independently optimized. Wouldn't it be nice if we could take this conventional model setup and represent it by one neural network? This would give us many advantages in terms of model simplicity, model size, and optimization is much easier now. So what I'll talk about is the advances that our team has made towards end-to-end models for speech recognition. So first, let me get into a historical development of end-to-end in our field. Connectionist temporal classification, or CTC, was one of the first end-to-end models that was explored by Alex Gray and others in 2006. So CTC introduces a special symbol, blank, which is denoted by capital B. And what it does is, given our input features X, it maximizes the probability of P of y given x by maximizing the total probability of the label sequence by summing over all possible alignments. Because of this, we don't need any frame level alignment. CTC was first explored as an end-to-end model around 2014 by Alex Graves et al., where he looked at outputting character-based units, which could then be easily combined into words. Others then looked at incorporating external language models integrated with CTC. Later work looked at large-scale GPU training, data augmentation, and multiple languages. And more recently, people have looked at CTC with longer span units, such as words instead of characters. And of course, there's been many, many others. Then around 2015, William Chan, Jan Krauski, and others looked at attention-based encoder-decoder models, perhaps one of the most popular being the listen, attend, spell model, or what we call LAS. In these encoder-decoder models, we first take our input features X, we pass them to an encoder to get a higher level feature representation. This is analogous to an acoustic model. And then, in the attention mechanism, we look at encoder frames that are relevant to predicting the current output and focus our attention on this. So the attention is very similar to an alignment model. Finally, the decoder takes the previous prediction, yu of y minus 1, and the attention context vector, and autoregressively predicts the next output token, yu, as a function of previous tokens and input x. One of the first things we wanted to look at was how does CTC graphing and attention-based end-to-end models compare to our conventional model? And in this case, when we say online means that the model is streaming, that at each frame in time, we make a prediction. So our conventional model typically operates in an online or streaming fashion, and CTC does as well. So the first thing that we can notice is that the CTC graphing model, without any language model, performs very, very poorly compared to the conventional model. And part of this is because of the frame independence assumption in CTC. By contrast, the attention model, though it's offline, meaning it looks at the entire utterance before making predictions, has a much, much better word error rate than CTC, though it still lags behind a conventional model. So the next focus of our group was to take the attention-based models, and improve the performance relative to the conventional models. And so that's what I'll talk about next. And most of the work that I'll talk about can be found in the second paper here, Chu et al. So one improvement we did was to say, when we compute attention, where attention is focused on a very narrow slice of the encoder feature space, as we can see by the first single-head attention figure on the left here. Instead of computing a single-head attention, what happens if we have multiple attention heads? So we can focus on multiple parts of the input feature space when predicting the current output. We can think of this as passing a language model from the encoder to the decoder. And we can see from the figure that now the attention vectors are focused on multiple parts of the input space. Another improvement is to change our subword unit that we predict. So typically, longer units have a lower language model complexity. And in addition, longer units have better decoder efficiency. So for example, word pieces have 3 times as fewer units as graphemes, which means we don't have to run the decoder in an end-to-end model as often. So we looked at word piece units for this choice. This was first looked at by Mike Schuster in 2012 for some work in Japanese. And it has also shown good results for end-to-end models like Kanishika Rao. So the word piece model is trained to maximize the language model likelihood on a set of text-only training data. The model is position dependent, and the word pieces are determined deterministically. So if we take the sentence "good afternoon" on the left, the right is its word piece model tokenization, where this underscore is indicating the space, but we can see that it's tied to the position as well. In addition, word piece units back off to characters, which means we have no out-of-vocabulary words. Typically, end-to-end models are trained to optimize P of y given x, which is the cross-entropy loss. But in speech recognition, we care about word error rate. So we changed our training objective to actually optimize for word error rate through the minimum word error rate criteria. In this formulation, we minimize the expected number of word errors. And that's done by saying, for each hypothesis y, we weight it by the expected number of word errors. Finally, we look at various optimization improvements, such as scheduled sampling, where during training, instead of feeding back in the previous prediction, that is the ground truth, into the model, we sample from the model and feed a hypothesis. This helps prevent overfitting. In addition, we look at label smoothing, where we take the logic class that has the highest probability, subtract off a constant value, and smooth it over other labels. This also helps prevent overfitting. Finally, we look at synchronous training, where the gradient updates between workers are computed in synchronous fashion rather than asynchronous, which we have found leads to faster convergence and also better performance of the models. Putting all of these together, you can see that our conventional server-based model, which is 7.2 gigabytes, has a word error rate on a voice search task of 6.7. Our attention-based model, which is 18 times smaller than the conventional model, has a word rate of 5.6, around a 16% relative improvement. So this is exciting for us. We now have an end-to-end model that is better than server, but now the drawback of this model is that it's not streaming. It looks at the full context of the utterance before making predictions. So of course, our next challenge was to keep up with the quality improvement while having the model be streaming. So why is streaming speech recognition so important to Google? So when I speak a query, what's the weather like in New York? I want the words to appear to the screen right away. And I also want the microphone to be closed right away so that the hypothesis can be sent to the server for fulfillment and the answer can come back as quickly as possible. Oh, the weather is cloudy today in New York. Streaming speech recognition is critical to many of our products for good user experience. So we looked at many different types of streaming end-to-end models, and in the end, we settled on the recurrent neural network transducer. And in this model, you have an encoder network, which are like a set of recurrent layers, like an acoustic model, that take acoustic frames and give a higher level feature representation. We also have a prediction network, which takes the previous prediction and outputs a higher level representation as well. We can think of the prediction network as being similar to a language model and the encoder as similar to an acoustic model. We then have a joint network, which combines the acoustic and language model predictions. And this goes to a softmax, which outputs each subordinate. The model is optimized end-to-end, and of course, no alignment is needed. And one of the benefits of this model is that at each time frame, we either output the subordinate or we output blank. So the model is indeed streaming. Another criterion we have for online end-to-end models, not only is that the text streaming, but that we're able to endpoint or close the microphone as quickly as possible so we can send the request to the server for fulfillment. Typically, the way this is done in a conventional model is you have a separate voice activity detector, which detects where there's large changes from speech to silence and uses that to close the microphone. We can imagine that having an endpointer that is integrated into the end-to-end model is going to be better than a separate endpointer. So we looked at jointly modeling the end of utterance prediction with the rest of the hypothesis text with RNN2. So what we do is we penalize the end of sentence token, which tells us that we should close the microphone if it occurs too early in the sentence or too late in the sentence. With this, we improve the word error rate by with the RNNT endpointer compared to an RNNT with VAD from 7.4 to 6.8, with about a 70 millisecond improvement in the end pointer latency. End pointer latency in this case is when I actually stop speaking, how long until I actually predict end of sentence. So we want this number to be as small as possible. Now, one can imagine when we introduce these streaming requirements that we will take a quality degradation. So to make up for this, we looked at incorporating our attention-based model into this framework. But of course, the constraint is still that the attention-based model needs to operate within the allowable latency constraint. The way we did this is we have a shared encoder and a first pass RNNT decoder, which is streaming. So in the first pass, we output hypothesis YR, and then what we do in the second pass is we rescore that with a full context LAS attention model. And one of the reasons that we can run this quickly in the second pass is most of this computation, all the encoders and the decoder can be run in the first pass. So it's just the second pass decoder that has to be run in the second pass. With this, we get more than a 10% relative improvement with the LAS scoring compared to RNNT. Finally, if we compare to our conventional model, which has a first and second pass, which is around 87.2 gigabytes, has a word error rate of 6.6 on voice search, and has an end pointer latency of 870 milliseconds. The proposed on-device end-to-end model is about 100 times smaller, has a word rate of 6.1%, and has an end pointer latency of 780 milliseconds. One of the big goal that we had last year was to develop a streaming on-device end-to-end model that was better than server-side in both quality and in latency. And this model was launched on the Pixel 4 last year. And the feedback we got, this is a quote from The Verge, for example, is that you can ask the assistant to do things that are local to your phone, and they'll happen near instantaneously. It's much faster and needs to rely on Google Server much, much less. So just to quickly summarize, a few years ago, the team started looking at end-to-end models. We were able to develop an attention-based model that achieved state-of-the-art performance compared to a conventional model, but was not streaming. So then we addressed the streaming component by looking at the recurrent neural network transducer to help with streaming. And then to make up for the quality and latency concerns, we looked at RNNT-EP and a second pass LAS model. And with this, we were able to develop a system launched on Pixel 4 last year, which surpassed server-side performance in terms of both quality and latency. But of course, our work is never done. One of the challenges that we're dealing with now is how to improve performance on long-tail named entities and proper nouns, where conventional models still perform a lot better. Number two, simplify the ASR system by building one end-to-end model for multiple languages. So first, handling long tail. And I'm going to discuss one way that we do it with contextual biasing, but of course there's many ways to do it. So what is biasing? Biasing is an attempt to bake into the model some prior notion we have about the environment I may be in or who I am likely to call on my phone. So for example, if I'm in Boston, I'm likely to ask for restaurants in Boston or sports team scores in Boston. So biasing helps to incorporate this information into decoding, so we're able to better recognize words based on the context that we're in. And why is biasing so important? Here's an example of 3 different test sets: a contact test set, which is, call so-and-so on my phone; numerics, for example, navigate me to such and such an address; or a yes-no cancel set, giving specific yes-no cancel requests. And this is for a conventional model. And we can see that the word error improves by more than 10% relative across many domains. So the way we used to get biasing working was to use a shallow fusion approach, where we take the score from the end-to-end model, and we interpolate it with a biasing FST, where the biasing is done only at test time. And here lambda is an interpolation weight that we tune for each biasing task independently. The first two columns show for this context and songs. Songs is Play Me, this song by this artist. We can see that the conventional model for biasing and the end-to-end shallow fusion biasing are roughly on par with each other. So this is nice. We're able to at least have biasing within our system, which is coming close in quality to the conventional model. But how to improve a long tail named entity recognition for general queries without biasing is still a very open and challenging problem, particularly how to do this on device. Here's another area that we're working on with respect to dialect and multilingual systems. So in a conventional model, we have an acoustic pronunciation language model that is separately trained for each language. And we can imagine as the number of languages scale up, this becomes very difficult to maintain. People have looked at what's called conventional co-training, which is having one acoustic model for all languages or one pronunciation model for all languages, but offering a separate LM for each language. Wouldn't it be nice if, for sequence to sequence, we can have a single model for everything? Instead of having N phonemes, lexicons, language models, etc., this would be a lot simpler if we could have one neural network. And perhaps the joint optimization and the data sharing would even lead to improvements in word error rate. And finally, the infrastructure would be a lot simpler as well, without having to maintain all these separate phonemes and lexicons and whatnot. So we explored many ways to do this. And the way we settled on was to feed a domain ID, which passes language information into the encoder, which models acoustic variation, and potentially into the decoder, which models lexicon and language information. Our first task was explored on 7 English dialects, and we can see from the figures below that they're unbalanced both in their data and in their target classes. The first row, the baseline here, is a model trained on each individual dialect. And we can see that we get improvements in word error rate when we train a model on all of the languages together and feed it to the language ID to the encoder and decoder. But the best setup is to feed it to both, and that gives us the largest gains. And most importantly, when we feed it to both, the performance of the joint model is better than a model trained on each individual domain. We similarly repeated this for Indic, where we had 9 Indian languages. And I think one of the additional challenges with Indic is that these languages varied in their script. And we can see that the dark blue is the joint model, a model trained on all of the data. And the word error rate here is better than an individual model trained on each language separately. So again, co-training is better. And the plot on the right is showing that when we feed in the correct domain ID, the model remains very faithful to its script. So we're able to build end-to-end models for multi-dialect or multilingual, but how to scale this up to many languages, particularly when the families are disjoint, is still an open and challenging research question. And with that, thank you for listening.
All right, hello. I'm so excited to get the opportunity to talk to you all. My name is Jen Wortman Vaughn. I am a senior principal researcher at Microsoft Research in New York City, and I will be talking to you from my home in Brooklyn. I'm very sorry that I can't be there in person speaking to you all today, but I hope to get that opportunity another time. And I can't wait to tell you about my work on intelligibility throughout the machine learning lifecycle. Today, I'm going to be talking to you about my work on intelligibility throughout the machine learning lifecycle. Now, if you're watching this, I probably don't need to waste my time convincing you that machine learning is important. But throughout this talk, I'm going to be arguing for the importance of taking a human-centered view of machine learning. Now, before I get there, let me just back up a moment and tell you a little bit about myself and where I'm coming from. So my research training was in two areas, machine learning theory and algorithmic economics. This means that I've spent a lot of time over my career designing algorithms and proving formal guarantees, and I still do some of that today. But now I spend most of my time on human-centered approaches to transparency, intelligibility, fairness, and responsible AI more broadly. So how did that happen? Well, I can trace my interest in these topics back to 2016 when I went to DC for one of these panels on AI and society that are happening all the time. One of the panelists made this claim that soon our AI systems will be so good that all of the uncertainty will be taken out of our decision making. Now, to me, this was a horrifying thing to claim. The world is full of uncertainty. All of our AI systems and machine learning models have uncertainty baked into them, whether it's explicit or not. It's just irresponsible to tell people that AI could take this uncertainty away. So I came back to New York fuming and immediately ranted about this to my colleague and good friend, Hannah Wallach. Now, Hannah and I spent the next month or two dissecting this claim and why it bothered us so much. This was around the time that there started to be a lot of talk about democratizing AI, making it easy for lay people to build and deploy their own machine learning systems. It was also around the time that Hillary Clinton's chance of winning the US election was hovering around 80%, and the general public was treating this like a done deal. Watching all of this play out and replaying this panelist's quote over and over in my mind, I became obsessed with this question of how well people really understand the predictions coming out of models. As a machine learning theorist, I was trained to always state my assumptions clearly and explicitly. The stating of assumptions was just really core to what I do. And I was afraid that people may not always understand the implications of assumptions that are going into machine learning models, or the uncertainty behind predictions. These worries led me to discover the literature coming out of the machine learning community on intelligible or interpretable machine learning. I'll use these words interchangeably in this talk. And I got really hung up on the fact that people were designing these methods without stopping to define exactly what they mean by interpretability or intelligibility, basically proposing solutions without first defining the problem that they're trying to solve. So I started talking about this with colleagues with backgrounds in psychology and other human-centered fields, so people who know about behavioral experiments and about user studies and so on. And I started running experiments to see how interpretability plays out in practice. I ended up getting really excited about this research area, and now it's one of the major themes of my research. So why should we take a human-centered approach to intelligibility? Well, we often think about machine learning, and we often teach machine learning as this fully automated process. We take some data, we use it to learn a model, and out come these automated predictions. But one thing that I've learned over the years is that people are at the heart of the machine learning lifecycle. People define the task that machine learning will be used to solve. People decide which data to collect. They decide how to pre-process the data and how to label it. And the data itself is often generated by people, either explicitly, for example, through crowdsourcing, or implicitly, for example, if the data contains images of people or text that people have written. People determine the model to use. So should we use a neural network, a random forest, a linear model, something else? People choose how to train the model. how to test the model, which may require gathering more data from additional people. People make choices about whether, when, and how to deploy the model. And of course, the deployed models end up impacting people's lives, sometimes in high-stakes domains like medicine or finance. And finally, feedback from these people is incorporated as the model evolves. So given the central role that people play in the machine learning lifecycle, I take the position that building machine learning systems that are reliable, trustworthy, and fair requires that relevant stakeholders have at least a basic understanding of how they work. Now, the approaches to model intelligibility coming out of the machine learning community generally fall into two categories. So the first type of approach is to design or deploy transparent or glass box models that are intuitively simple. So simple here might mean something like a small decision tree or a sparse linear model. Just as one example, my colleague Dan Goldstein and his collaborators have some really nice work on simple point systems that a decision maker like a judge can memorize and apply on the fly without even a pencil or paper. They show that in many high-stakes domains, at least when you have tabular data, these point systems are nearly as accurate as complex models like neural networks. As another example, my colleague Rich Caruana has a body of work on generalized additive models, or GAMs, that falls into the same category. The reason that GAMs are nice is that predictions have this additive structure, which allows users to visualize the impact of a single feature. So you have one function corresponding to each feature, like the one I've shown here, and you can visualize that function. The second common approach is to design simple post hoc explanations for complex models. You may have heard of LIME or SHAP, and I would put these into this category. Now, many of these approaches work by approximating a complex function using a simple local approximation like a linear function that can be easily explained. SHAP, which I'll come back to later, builds on ideas from cooperative game theory to assign an importance to each feature, which is intuitively a measure of how much the feature contributes to a particular decision or prediction. But despite all of this really cool research going on, there's still a fair amount of disagreement in the machine learning community about what intelligibility means and how to measure it. Looking at the proposed approaches, it's natural to ask what makes a model or explanation simple? How is simplicity related to intelligibility? Do these models actually help users achieve their goals? There have been a couple of position papers examining this issue, and as Finale Doshi-Velez and Bean Kim have pointed out in theirs, the machine learning community often has this "you'll know it when you see it" attitude. The difficulty of quantifying intelligibility is compounded by the fact that there are different types of users or stakeholders, and these users have different needs in different scenarios. So the approach that works best for a CEO making strategic decisions is likely to be different than the approach that works best for a regulator who wants to understand why an individual was denied a loan. And this in turn may be different from the approach that works best for a data scientist trying to debug a model. Additionally, all of the approaches I've mentioned so far have focused on intelligibility of the model itself. But if you think about this picture of the machine learning lifecycle that I showed earlier, model intelligibility is just one piece of a bigger picture. Depending on who our stakeholders are and what goals they may have, we may want to introduce intelligibility at other stages of the machine learning lifecycle, starting from definition of the problem being solved and data collection all the way through model deployment and feedback. These concerns have prompted me to adopt a human-centered agenda for intelligible machine learning. And I should mention my colleague Hannah Wallach and I have recently written a book chapter on this agenda, which you can find on my website. So if you're interested, you can check that out. Now, within the FATE group at Microsoft Research, we've been working on this agenda from several angles. So first, we propose that people stop relying on intuition alone and instead empirically test which factors of a model enable users to better achieve their goals. In a few moments, I'll tell you about some work we have in this space that examines how factors commonly thought to influence the intelligibility of a model impact people's use of the model. A second angle is to consider intelligibility beyond models. So, for example, intelligibility of data or objectives or performance metrics. And I'll tell you about some of the work that we have in this space, examining how the stated and observed accuracy of a model impacts people's trust. Another example, which I won't have time to go into today, is our work on data sheets for data sets, a project on data documentation for responsible AI. Finally, we propose that people design and evaluate methods for achieving intelligibility in context with relevant stakeholders. Here, I'll tell you more about recent work examining how data scientists perceive and use intelligibility tools. Okay, jumping right into this first point. To question our intuition about intelligibility and empirically test it, my colleagues and I found it helpful to think about intelligibility as a latent property that can be influenced by different manipulable factors, such as the number of features in a model, whether the model is linear, the user interface, and so on. And that impacts different measurable outcomes, such as the user's trust, ability to debug a model, or ability to simulate the model's predictions. Notice that all of these properties on the left here are properties of system design, whereas the properties we have on the right are properties of human behavior. Now, taking a cue from psychology, in a project led by Farooq Poursabzi Sengda, we designed randomized human subject experiments to isolate and measure the impact of different system factors on the fundamental properties of human behavior relevant to intelligibility. In our experiments, participants were asked to make predictions about the selling price of different apartments with the help of a model. In addition to a simple baseline in which participants did not have access to any model, we considered 4 experimental conditions in a 2x2 design, corresponding to the 4 models you see here. Now, I don't expect you to be able to read everything on the screen, but let me point out the differences between conditions. So the models on top use 2 features, while the models on the bottom use 8. The models on the left are black box, while on the right you see transparent linear regression models with weights that are visible to the participants. And for these conditions on the right, we explained during a training phase exactly how these models work. Now, crucially, in all of these conditions, participants see the same model input, so the same apartment features, and the same model output, so the predictions. That is, we specifically chose apartments where the 2-feature and 8-feature models made the same predictions. So the only difference between conditions is what people see in between. This means that if we observe differences in people's behavior between conditions, we can safely attribute these to differences in the model. This is super important to our design. I won't go through our results and studies in detail, but let me mention just a couple of key results and implications, and I'll point you at our paper if you're interested to learn more. So first, we found that participants who were shown a clear or transparent model with a small number of features were best able to simulate the model's predictions. This is perhaps unsurprising, but reassuring to see in the data. However, we found no improvements in the degree to which participants followed the model's behavior on typical examples, when it generally would have been beneficial for them to do so. Additionally, we found that in some cases, too much transparency can actually be harmful. Specifically, transparency reduced people's ability to detect when the model made a sizable mistake and correct for it, seemingly due to information overload. This was really surprising to us. And more generally, these results just emphasize the importance of user testing and experimentation over intuition in the design and evaluation of intelligibility models. Okay, moving on to the second direction, intelligibility beyond the model. Let me briefly mention some work of ours led by Ming Yin, who is now at Purdue, that received a Best Paper Honorable Mention at CHI this past year and can be viewed as a study of intelligibility of performance metrics. So in this study, we set out to examine whether a model's stated accuracy on held out data affects people's trust. If so, whether it continues to do so after people have observed the model's accuracy in practice. And finally, how the model's observed accuracy in practice affects people's trust. To do this, we again made use of randomized human subject experiments. We showed subjects information about pairs of people who had been matched through a speed dating event. Subjects were first asked to make their own prediction about whether a speed dating participant wanted to see his or her partner again. They were then shown a prediction from the model, and finally they were given a chance to revise their original prediction based on what they saw from the model. They did this many times, completing 40 such tasks in 2 phases. So at the beginning of the first phase, we gave them information about the model's accuracy on held out data. Then, after the first phase, we gave them feedback on how they themselves and the model had performed so far. At the end, we had them answer a few questions about their use of the model. In each of these experiments, we varied either the stated accuracy or the observed accuracy of the model, or both. So these were what we were varying in our randomized conditions. Again, I'll skip right to the high-level results and implications for today and point you at the paper for more detail. So first, we found that the model's stated accuracy on held-out data does affect people's trust in the model, and specifically that they're more willing to depend on the model when its stated accuracy is higher. We also found that people put substantial weight on their own interactions with the model and the accuracy that they observe. So we saw this happen even though subjects had somewhat limited interaction with the model. That is, they changed their behavior after getting information about how the model performed only on these 20 tasks in phase 1. These and the other results that we discuss in more detail in the paper highlight the need for designers of machine learning systems to clearly and responsibly communicate their expectations about model performance. We see that this information shapes the extent to which people trust the model, both before and after they're able to observe and interact with it in practice. And we go into this in much more nuance in the paper. Okay, moving on to the final bullet here. I'll spend the last few minutes talking about some recent research looking at how we can evaluate the intelligibility of existing tools with stakeholders in context. This work was led by an incredible summer intern, Harman Tower, and received a Best Paper Honorable Mention at CHI 2020. In this work, we're zooming in specifically on data scientists building models as our stakeholders of interest. In particular, we're interested in how data scientists perceive and use existing off-the-shelf intelligibility tools, what challenges they face, and what opportunities we have to make these tools better. Before I get into this study, I want to step back and talk about why this type of evaluation is challenging. And I want to be super clear here that the reason that this type of evaluation is often missing from machine learning papers is not because machine learning researchers are lazy or just don't care, but because getting this type of evaluation right is really an entire research agenda on its own. Okay, so first, this type of study requires expertise in both machine learning and in HCI or psychology or other human-centered areas. It requires knowledge of both the academic literature, but also day-to-day engineering practices of data scientists. It requires both qualitative analysis to understand the nuances of how tools are actually used in context, and a balance of quantitative methods to scale up and yield reliable findings. A study should mimic realistic data analysis settings, but not be too cumbersome. And it requires separating out effects of the model, the intelligibility technique, and the user interface of a specific tool. So to address these challenges, we recruited a diverse team of researchers and practitioners and so on to work on this project. So machine learning researchers, HCI researchers, and data scientists. And these data scientists have practical experience both building and working with intelligibility tools. We also attempted as best as we were able to put the data scientists we studied in a realistic context. And you'll see more of that in a moment. And finally, we used a mix of qualitative and quantitative methods. Specifically, we started with pilot interviews to identify challenges the data scientists face in their day-to-day work. We then ran an interview study in which we observed data scientists' ability to use existing interpretability tools when faced with the types of challenges we extracted from the pilot. And finally, we ran a large-scale survey with about 200 data scientists to scale up our results. So for the preliminary interview study, participants were put into context, in this case, working with real data, a real model, and a real intelligibility tool with a Jupyter notebook. We wanted to explore the use of both types of tools I mentioned earlier, so simple models and post hoc explanations. So we had half of the participants using generalized additive models, or GAMs, and half using SHAP. Participants saw a tutorial on the interpretability tool that was based on existing published documentation with a bit more detail added. Then they saw a trained model with visualizations from the interpretability tool. And finally, they answered some questions about the model. So each of the tools, GAMs and SHAP, provided three types of explanations. The first is local feature importance. So a description of how important each feature is for the prediction made on an individual data point. The second is global feature importance. So how important is each feature across the whole data set? And the third type of visualization zoomed in on the way that a specific feature, age in this case, impacts predictions. The model was trained using a variant of the adult income data set that was modified to reflect the types of challenges we extracted during the pilot. So for example, we saw that data scientists often face problems due to the way that missing values are filled in. So before training the model, for 10% of our data points with positive labels, we removed the age value used and used the common approach of replacing it with the mean age across the data set, which in this case was 38. And this resulted in a model exhibiting a strange jump in predictions for 38-year-olds. Okay, a couple of different themes emerged from our qualitative analysis of the interview data. So first, we found that there were a set of participants who overused the tools, using them too much to justify cases where the model exhibited strange behavior. And this led them to place too much trust in the underlying model. As one participant who was given GAM said, age 38 seems to have the highest positive influence on income based on the plot. Not sure why, but I guess if that's shown, it makes sense. Another participant who was given SHAP ran some tests on their own and was willing to accept the model's behavior when those tests agreed with SHAP's output. On the flip side, we also saw some cases in which participants underused the tools because they weren't confident about exactly what the tool was showing them. Another theme that emerged was the importance of social context. So in particular, participants seemed willing to trust what the intelligibility tools were telling them simply because they were publicly available tools. And as you can see here, one kind of explicitly said this. Now, to scale up these results, we ran a large survey mimicking the interview setup as best as we could. We took advantage of having a larger pool of participants to run some randomized controlled experiments. We randomized two things. First, we randomized whether each participant used generalized additive models, or SHAP. And second, to understand how people were affected by the content of the explanations themselves, we randomly showed half the participants a manipulated version of the global feature importance values, in which we showed the less important features as more important and vice versa. Our qualitative findings on the whole were similar to what we saw in the interview study, although some additional themes emerged. I'm running low on time, so I'll skip over this. I'll just highlight a couple of our quantitative findings. So first, participants had higher accuracy on multiple choice questions about visualizations using GAMS compared with SHAP. Participants using GAMS were also more confident compared with those who used SHAP. And we saw that manipulating feature importance values reduced participants' confidence that the explanations were reasonable. So this is a good thing, right? They're less confident when we show them the manipulated explanations. But on the other hand, we saw that this did not lead to increased suspicion about the model or the interpretability tool as we would have expected. Okay, so this work suggests several next steps for the research community that I'll just quickly highlight here. First, we need more interaction between machine learning and HCI researchers, and we need it to happen earlier. Second, we need more tools that are designed to encourage deep thinking and discourage people from making snap judgments. So as one of our participants really nicely put it, there's this concept in UX called thinking fast and slow. And while these visualizations are made to make me think fast, every detail about them requires that I think slow. Finally, in our study, we had only about half an hour of time from each participant. And the community really needs more long-term studies to explore how understanding and usage of these tools changes over time. Okay, popping up a level, I've told you about studies that we ran on lay people and data scientists, but there are many other stakeholders who might require intelligibility. And a huge wide open direction for future work is to better understand the needs of these stakeholders and how to design approaches to help them. Finally, we just need to take a broader view of intelligibility, as I've argued, and think about how to bring intelligibility to every stage of the machine learning lifecycle. All right, thank you so much for having me. And yeah, that's all. Thank you.
Thank you, Dr. Ham, Dr. Sainas, and Dr. Vaughn. Now, the presentation session is over, and now it's time for the panel discussion. Let me introduce our 6 invited panelists. Professor Yoshua Benjo is here, right? And Professor Jan LeCun is here, okay? And Professor Chelsea Finn is here, and Dr. Tara Sainas is here, and Dr. Jen Waltman Vaughn is here too. Lastly, we invited a special guest, Dr. Inyop Kang, the president of System LSI business of Samsung Electronics. Dr. Kang, could you introduce yourself shortly?
Yeah, this is Inyop Kang, the general manager of System LSI division in Samsung Electronics. It's my great pleasure to join this forum. Let me go by saying I feel like standing on the shoulders of a giant. Thank you.
Thank you. So further discussion, there will be a natural way to discuss, but we prepared short discussion items pre-hand. So let me start with some suggested discussion topics first. Let me talk about question on big neural net models, which is a hot passion now. As shown by GPT-3 of OpenAI, bigger and bigger models are being developed, as you know. Can we handle this explosion with current computing hardware of deep learning, such as GPU, or do we need new architectures of computing? Any ideas?
Hello. I mean, it depends if you're working in academia or industry. And so if you're in academia, I can tell you that we would really appreciate some progress on the hardware to be able to run larger models and learn on the scale of things like GPT-3. On the other hand, what I'd like to add is there are lots of very exciting and important research problems that we can address without having that kind of computing power. If you look at some of the open problems that I discussed in my presentation, many of them are already challenging, even in very simple environments. And so, yeah.
Okay. So, Dr. Kang, as a head of making processors, do you have any idea about this evolution of
I need to understand the amount of horsepower they use in the GPT-3. All I know is they used 175 billion parameters. Anybody has an idea what kind of hardware they use or how much money they spend? Depends on that one. I could answer, I guess.
So it takes a lot of resources, and the specific number is not known here, but people say that the cost of training GPT-3 is more than 1 billion, not 1 billion, but $100 million.
So, the parameter they said is 175 billion parameters.
Yes.
So I'm just wondering, there's a trained parameter, I assume.
Yes.
But what kind of hardware they're going to use for the interactive, the NLP, is sort of should be real time. So I'm just wondering. So, and then somebody criticized GPT-3, they are lacking causal understanding, even though some others say it's wonderful in terms of article writing. It's hard to distinguish whether it's from real human or not. But I have a little idea. But at the end of the day, I think we need one more step, not just like a current approach.
Right.
I mean, that's why Professor Benjo is working on system 2, right?
That's right. So, in that case, let me go to the related topic with this question. So, the idea is that could modularity and compositionality of neural net be a way to overcome this big computational bottlenecks of big models? If so, could neural net modules having different functionality be emergently discovered in self-supervised way? Is that, do you have any word on it, Dr. Benjo?
Sorry. Yes, I think the main advantage of modularity is for out-of-distribution generalization, right? So if you can decompose the knowledge that is learned in pieces that can be recombined, especially in novel ways that may have not been seen during training, then you're increasing your chances of being able to do out-of-distribution generalization or fast adaptation. And we now have a series of papers suggesting that this hypothesis makes sense and that you can get better transfer learning or adaptation or even zero-shot generalization. But it's not easy, and I think we're just beginning to explore these kinds of architectures. Another interesting connection is between modularity and causality, because if you study a bit of the causality literature, what it tells you is that there is, in principle, an ideal, correct way of decomposing knowledge into pieces corresponding to the underlying mechanisms, the so-called independent mechanisms that can be separately learned and sort of factored from each other.
Maybe this kind of modularity can help the intelligibility itself of these models, because the big end-to-end models like GPT-3 it's very difficult to understand what's going on inside here. So, okay, any other?
Yes. Yes, I think that this kind of modularity may also not be applicable everywhere in the system. Like, what's plausible is that you only are able to do it at sort of a high level of abstraction for the kind of knowledge that we communicate with language, but it may not apply for things like perception, for which it might be potentially intractable to get the sort of interpretability that allows us to explain with words what we're doing and how we're reasoning.
Okay. Let us talk about a little bit more about these big models. So as Dr. Kang mentioned, GPT-3 has 175 billion parameters, and it shows amazing versatility already. But human brain is a lot larger. Human brain is known to have 100 trillion synapses. If we scale up current neural nets up to the level of human brain, could we achieve human-level performance? Some people argue that, but do we have to focus on scaling, or rather than searching for new algorithms and new architectures at this point? Do you think?
Let me answer.
Okay.
My daughter always said that on this kind of question, my daughter's answer was BOTH, both. We gotta try both.
Yes, we have to go both.
Either one. Yeah, sure thing. As a matter of fact, since I'm gonna have this forum, I calculate based on the known literature how many the cortex neurons we have, how many synapses, human synapse around 15,000 connections per neuron, and calculate how much money do I need, how much silicon area I need. And roughly, it depends. It depends on scaling. It requires 1 kilometer square to 10 kilometer square. It requires $100 million to $1 billion. So that's a very back of the envelope calculation. So eventually we're there, but I'm kind of doubt we can achieve a human level using existing silicon technology. So in that sense, definitely we need to have new algorithms as a complexity reduction, I think.
If I may answer that question. Can you guys hear me okay?
Yes, we hear you clearly, yes. Although we don't see your face.
I know you can't see me, and I'm not sure why, because my video is on, but somehow it doesn't show up. Anyway, I think we're missing some major pieces to be able to reach, human-level intelligence or even sort of animal-level intelligence, like, the level of a cat or a dog. I think we're missing some, very basic principles that we haven't yet discovered. And it's not just a matter of scaling the methods that we currently have. A cat brain has about 800 million neurons, so it's not that large. We might have machines in the near future that are able to reach that scale, even though the number of synapses is very large. But the point is that we just don't have a good idea for what learning algorithms nature uses. And the type of, the paradigm of learning I talked about in my talk, self-supervised learning, is not something that we're doing very well with machines. We're not able to really reproduce the type of learning that we're observing in animals and humans. So until we figure this out, I don't think we have any hope of kind of reaching the type of intelligence we observe in animals and humans.
Yeah.
I agree with Jan that there seem to be fundamental things that we are missing. I think that GPT-3 systematically makes certain kinds of mistakes that won't be addressed with a larger model. In particular, as one example, I think we need to think more about the data that these systems encounter. For example, if something changes about the world, like the COVID-19 pandemic, a static GPT-3 model will not be able to intelligently speak about some of the things that have changed without completely retraining the model on all sorts of new data. And GPT-3, for example, doesn't know how to interact with humans in a way that allows it to adjust its knowledge. And it doesn't have an understanding of the consequences of what it says, kind of a sort of like sequential decision making. So I think that there's all sorts of limitations of GPT-3, especially with regard to the data that it's trained on, that are missing. And we need to be thinking about, I mean, I kind of agree with the sentiment of trying both scaling models more and trying new techniques, but I think that we're not going to get there with just scaling.
Yes, yes.
Question then. So you guys think inferencing-wise, we're in good shape. But training, there's a massive network. We have no idea. That's what you guys saying, right?
I think what Jan and Chelsea are saying, and I agree with them, is that even if we're able to scale up even more than we're doing now, we would continue having diminishing returns and never converge to something, anything close to, say, what a 2-year-old could do. And as Chelsea was saying, part of it is because there's a lot of knowledge about the world that, say, something like GPT-3 doesn't have even access to. I mean, just training on text does not allow the machine to understand how the world works, because there are a lot of things that we can't about, a lot of knowledge in our head that is not verbalizable. And so we can't write it down. And so GPT-3 can't learn about it. And so future systems that have intelligence comparable to a child or an adult will need to build a world model similar to what Jan was talking about, understanding how the world works, mostly in an unsupervised way. I think they will have to be like babies and go after that knowledge in an active way. But in any case, it's a lot of open questions that we still have to study, and we have no clue when it's going to be solved.
Okay, so we have a related question about how can we bridge the gaps between the current technology and the future of human level intelligence. So it says that, what are the current limitations of machine learning, even in the age of GPT-3? What are the gaps between current machine intelligence and real human intelligence? How can we build a bridge between them? It's kind of related with that, right?
I'll jump in here. So in my mind, GPT-3 can generate coherent text, but there's a big difference between language generation and truly being able to understand what it is that's being said, right? And because of this, machine learning models are going to make types of mistakes that are just very different than the types of mistakes that are made by humans. And this can have really devastating consequences if these models are used in high stakes scenarios. This is going back to what Chelsea was saying a minute ago, actually, about language models not understanding the consequences of what it is that they're saying. Language models are known to generate text that's offensive or text that is even dangerous if we're thinking about something like a medical application. So in my mind, in the short term, at least, rather than just trying to go for technical approaches to try to bridge this gap, I think we need to go for more social approaches as well, and think about things like adding human oversight if necessary, if we're thinking about using models in something like these high stakes applications.
Maybe I can add to a little bit of what Jen said as well. I think a lot of these machine learning models that we're looking at, they are great at memorizing the training data that we give it, but they don't generalize well to, like in speech recognition, they don't generalize well to words we haven't seen. And so, for example, we see with our end-to-end models, they do great on the 200 million examples that they're trained with, but you give it some out-of-domain vocabulary word and it can't even recognize it. Whereas humans don't have that same generalization problem like these end-to-end models do. So another challenge is, how do you adapt or inject knowledge in a quick way without having to retrain a whole model every time there's a new word that you don't get right? And this is challenging.
Dr. Benjo, you have a few words.
Yeah, I mean, I agree with everything that was said, and I want to make a connection with what we talked about earlier with GPT-3. So, as Tara said, and you know, very much in line with Chelsea's talk, one of the big gaps is fast learning of new tasks, or even zero-shot generalization. Humans are very good at that. We are faced with a new environment, and we kind of understand what's going on, even though it doesn't look anything like we've seen before. So it's not a matter of scaling here, right? It's not like we're not interested here in the asymptotic performance of if I have zillions of examples of the same distribution, but rather how you can face a new distribution, a somewhat different environment. Or in the case of speech, as Tara was saying, even the tail of the distribution is something like kind of exponentially rare individually. And so, yeah, scaling is just not going to cut it here. And we have to solve these problems, including the understanding problem, which has to do with understanding how the world works, related to causality and related to capturing the dynamics and decomposing knowledge in the right pieces. All of these things are not about scale. At some point, of course, when we want to deploy models that are understanding our world, and our world is extremely complex, we will need scale. But before we get there, there's a lot of basic science that needs to be done that could be done on a small scale.
I agree.
I completely agree with what's been said so far. One additional thing that I'd like to put out there, and one kind of additional thought is, I work a lot on robotics and actually trying to translate these machine learning techniques to build a physical robot that can operate in the world and do basic tasks in the world by interacting with objects. And while we've seen really impressive feats in AI and machine learning, from things like GPT-3 to playing chess to playing Go and so forth, we still don't have machine learning technologies and artificial intelligence capabilities of enabling a robot to make a bowl of cereal or drive to the grocery store. Like these really, really basic things are still beyond what our current algorithms are capable of. And I think that this is evidence to the fact that we're missing something fundamental about some of the things that are just so easy and intuitive to humans are actually so difficult for artificial intelligence systems. And we need to be thinking about how we actually solve the things that are easy for humans to do, like being able to generalize seamlessly to new environments and interact with objects, more so than figuring out how we can build very specialized systems to solve one task.
Great. So
Let's have some speculation. What are those missing links? Or you guys should try more. Oh, yeah, your video is on now.
Yes.
Or you guys should study primitive animals, trying to guess what are those missing links, like a neuroscientist?
Well, this is pretty much the content of our talks, actually.
I'm sorry. I mean, in a gist, in a single sentence, what are the speculations? I mean, they wanted, you guys said comparing to Homo sapiens, but if you compare to a very primitive one, we could guess, right? And some of the maybe the pre-programmed through the evolution link or whatever, right? At the end of the day, isn't that just the connection of atoms or molecules? That's it, right? If you think materialistically. Nothing else. There's no spirit, let's say.
We don't know.
So you know, in his talk, Jan insisted on the ability to learn from observations is something that we don't do nearly well enough. And Chelsea talked about the ability to learn from very little new data by almost learning how to learn. And I've talked about how being able to generalize quickly might be one of the advantages we get out of conscious processing that's more sequential and that we can verbalize with language. So these are all examples of directions that are actually very closely related to each other. that try to address these gaps that we've been talking about.
Maybe the capability of inferencing and the system 2 perspective of cognitive abilities may be a key to the missing link. So let's talk about something about system 2 ideas. The topic is humans have built civilizations by abstraction, such as math and sciences, and we created a lot of rules, such as laws. If we can effectively build the AI system who can have system 2 capabilities to build its own rules and abstractions, could AI augment human society itself by providing new abstractions and new rules? It's a kind of futuristic question.
Yes. Well, okay, so first of all, you have to realize that most of our work in machine learning these days is not about learning hard rules. Even
Yes.
the kind of system 2 research that I'm looking at isn't creating the kind of logical, symbolic, very easy to express rules. I mean, we might get there one day, and there are people who are following more of this kind of direction. But yeah, this is science fiction. One thing that maybe is closer to more reasonable and achievable is using the kind of representation learning power of machine learning and deep learning as, if we make progress towards learning like system 2 types of abstractions, is to help scientists come up with abstractions that they hadn't thought about yet, right? So if you look at what are scientists doing, what have they been doing in the last few hundred years? They've been coming up with abstractions that allow to capture, for example, causal structure in the world without having to go into all the gory details of, with the position and velocity of each atom in the universe. And so these abstractions help to explain things in a compact way that can capture causal mechanisms without having to look at everything else that is going on in the world. And so I'm hoping that the sort of research we're doing eventually could become a tool for scientists to propose hypotheses for new theories or new abstractions that can help to model the world better.
Okay.
Understanding society is much harder.
Yes.
I'm trying, and really I'm about to say it's impossible, but anyways.
Yeah, it's difficult. Okay, my next topic is related with the previous question. If we go back to the history of AI, in the dawn of AI in 1960s, many AI researchers believed hardly in symbolism. For example, the General's Problem Solver by Simon, Shaw, and Newell. It brought the long AI winter, and connectionism appears to be flourishing now with deep neural nets. Could we expect the remarriage of symbolism and connectionism in the coming future?
Okay, if I can answer that question, can you guys hear me?
Please. Yes.
Okay, because I had to change computer so that you could see me. So the big question there is, and this is kind of related to the previous question about system 2, is how do we get machines to reason, right? And particularly, how do we get learning machine to reason? So how do we make reasoning compatible with machine learning? And the problem with sort of classical approaches, symbolic reasoning, is that it manipulates symbols with logic, and logic is very highly non-differentiable. So it's essentially incompatible with the type of learning that we're very fond of at the moment. So I guess the big obstacle is how do we make reasoning compatible with gradient-based learning, essentially with backpropagation or something similar to this, evaluating gradients. And that probably means replacing symbols by vectors or tensors or numerical objects, and replacing logic by continuous functions or differentiable functions at least. And long chains of reasoning will be of a different nature, be replaced by dynamical systems and something of that type. And so it breaks a little bit, a lot of what sort of classical AI people have been thinking of and advocating. Now, how to do this is not entirely clear. There's a lot of interesting work along those lines in sort of the idea that, if you have a recurrent network, it can sort of, produce long chains of reasoning, that, you may have recurrent networks that are configurable for the task at hand, and having multiplicative interactions, attention, things like this are things that are very useful for that. In fact, transformers kind of come close to this. So one of the things I said in my talk is that I think, for example, the future of computer vision will combine completely feed-forward models like convolutional nets with sort of object-based reasoning on top of it, probably implemented with things like transformers or whatever comes will come to replace it in the next few years. So that's the kind of stuff I believe in, but it's not entirely clear how to instantiate all of this yet.
Yeah. To summarize, the answer to the question is no. I don't think that it makes sense to imagine that we're going to take the classical AI symbolic logic stuff and just slap it on top of deep learning. It's just not going to work. And there are many good reasons. So Jan talked about the differentiability and learnability, but there are also other reasons. So one of the fundamental problems with the classical approach is search, exponential cost of search, right? And in the old days, people used heuristics, and they were handcrafting those heuristics. Now, this is something where the modern machine learning approaches based on neural nets and so on actually can be very good at. If you look at how AlphaGo is really structured, it exploits the system one like value function neural nets to cut down the search in Monte Carlo tree search. I think it could be done much more efficiently, but the idea is there, and you need really to combine the reasoning that looks at sequences of steps with abilities to efficiently figure out good candidates for these trajectories. And if you look at human reasoning and human problem solving at a conscious level, we don't need to look at many different paths in our heads when we are planning. It just comes to us, one or two candidates, and that's it. It's enough, and usually they're pretty good. So that ability to generate good candidates is something that's probably not happening at the kind of symbolic or verbalizable level, let's say, but rather as something that's more like system one and where you can't easily decompose it into small pieces that can be explained.
Okay, thank you.
I agree with all of that. I think that there are limitations of deep learning, but the path to addressing those limitations is not necessarily to introduce symbols. Another limitation of kind of more symbolic approaches, to add to the ones that Jan and Joshua mentioned, is that symbols typically impose very rigid abstractions on the problem that you're trying to solve. But in the real world, we need to actually very flexibly change our abstractions and our representations based on the context that we're in. So if we, for example, have the symbol or concept of a bike, if we are riding a bike, our representation of that bike may be very different than if we're fixing that bike or taking a picture of that bike. And so we need to be able to have this sort of flexibility. And I think that many symbolic approaches don't allow us to have that flexibility.
Okay, the answer is no. Thank you. So next question is for Dr. Bengio. Before the ideas of your neural causal models, discovering causal relationship between numerical variables have been tried by many probabilistic approaches, such as Bayesian networks by Dr. Julia Paul. Could you explain why the new way of neural causal model is promising compared to the traditional approaches?
There are different parts to this answer. So one is very straightforward and would like the causal mechanisms that are the building blocks of a causal model to be sufficiently flexible, and using neural nets for these parts seems appealing. So that's one thing. So in other words, the whole causal model is a big neural net that just has a modular structure.
Yes.
Another thing that is missing currently in a lot of the research in causality is, where are these causal variables coming from? So when you're a scientist and you apply causal science, like if you're a biologist or a sociologist, usually you're going to define yourself what the causal variables are, right? They're going to give them to the model, and these are going to be things you can observe directly. But if you're a robot or if you're a 2-year-old, you just have your sensors and your actuators, and somehow you have to come up with the right high-level abstractions by which you can understand, causal dependencies like gravity and force and stuff. And by the way, this happens well before language kicks in seriously, so before 2-year-olds. So we can do a lot of that causal understanding of the world well before our parents can explain it to us. So it's really unsupervised discovery of both like the mapping between low-level stuff and these causal variables, and at the same time how these causal variables are related to each other. And that's a very tough problem, and we just started to look at this. But I think this would be a contribution to the science of causality, which hasn't been really looked at in the past, and where deep learning researchers, because they focus on representation learning, could really help to advance the science.
Okay, thank you. So next we go to some general issues of AI. This topic is, our society has inherent limitation in fairness. We live in unfair world, actually. Machine learning systems learns from this biased data. How can you make AI fairer? Should we augment the data, or should we change our society fundamentally in some way? How do you say? Both?
So I spend a lot of my time these days talking to product teams about fairness. And one thing I can say for sure is there are no easy answers to this one. On the question of data augmentation, data is part of the problem here, but it's not the only problem by any means. So data augmentation can only go so far, right? Really, if we want to build machine learning systems that are fair, we need to rethink the entire way that we're building machine learning systems and rethink who is in the room when that's happening. So right from the start, when we're defining a new product or a new service, we need to step back and assess possible unintended effects and consequences of that service. Systems are always going to reflect the values of the people who are designing that. So we need to ask, when we're designing the system, who is it giving power to, and who is the system taking power away from, right? And we should be willing at this point to step back and call off a product or change what we're doing if it seems like the harms are going to outweigh the good, or if we're in a case where the risks are just too high. Just because we can build something doesn't always mean that we should build this thing. There are, of course, things that we can do about data as well. When we're collecting data, we need to think about where this data is coming from. We need to think about the extent to which it represents different populations and where societal biases might be hiding. Are there biases that could arise from the technology that we're using to collect the data? Are there biases that could arise because there are humans labeling the data? other places in the process, this comes up too. When we're building a model, are there biases coming in because of the way that we've selected features or because we've chosen a particular objective function that might make some sense for some populations, but not others? I think all of this really requires a different style of thinking than machine learning researchers and data scientists are typically used to engaging in. And this means that we really do need to change who is present and whose perspectives we're hearing when machine learning systems are being designed and when all of these crucial decisions are being made. So we need more diversity. We need to have user researchers in the room. We need to have perspectives from people who will be using AI systems represented and perspectives from people who will be affected by these AI systems, especially when these happen to be marginalized communities. On the other side of the question, yes, of course, it would be better if we could just change society fundamentally, but this seems a lot harder to do, and there are things that we can do as computer scientists and as people building the systems to make some change.
To add something.
Scheduling algorithm, right? Scheduling algorithm, you have a fairness metric, but how are you going to define the fairness metric? That will be a tough one. I think we got to have a metric first, isn't it? Or we learn the metric somehow.
I think in general, there's actually too much of an emphasis on metrics when it comes to talking about fairness. Just, again, as computer scientists, and especially computer scientists who work in industry and are used to having everything judged by metrics, there's this kind of push a lot of the time to try to come up with metrics for everything. And sometimes this can actually be harmful when we're talking about fairness because abstraction is not always a good thing here. And if we're talking about systems that produce offensive text or that denigrate people or, there's just a lot of things going on that you can't cleanly capture with metrics. And sometimes we need to move beyond this.
I just want to add something to what Jen is saying regarding the second part of the question about society. So many of the things she talked about are about, changing the ways that, say, companies are designing and deploying AI to address some of the fairness issues. But sometimes or often, this will come at a price. And there may be some companies that decide to go ahead and pay for that, maybe because their brand is very important, their public image is very important. But there will be others which won't. And so I think that, society needs to change in the sense that changing the rules of the game, changing the incentive system, the fiscal forces that change the behavior of companies so that they will actually implement those policies that lead to, better protection of the public, making sure that their actions are not going against public good, and so on. So you really also need governments to step in, and today most of them are clueless about how to do this. So this has to be done carefully and probably consulting with the experts. But this is happening all around the world right now. Many people are discussing how this could be done, and countries are trying to align how they could do this. But at the end of the day, I think it's going to be better for companies as well, because at least the rules will be clear, and you won't be kind of in tension between your own personal moral instincts and the urge to survive, which company you're faced with.
Thank you, Dr. Benjo.
I agree with that to a large extent. And even within companies where people have good intentions and, either individuals or higher ups have good intentions, it still can frequently be the case that when people are under a lot of time pressure and need to make a decision about something that is shipping right away, fairness is still kind of the first thing that gets cut if there's no governance in place and no forcing function making this happen. So I agree. I just hope, given that there are really no one-size-fits-all solutions or even definitions for fairness, I hope that if there are external bodies that are making this type of governance that's going to apply to companies, they are not being too narrow in the types of definitions or limitations they're trying to impose. And if anything, I would rather see this type of regulation around processes or standards around processes that people should follow in the design of machine learning systems, rather than trying to make everybody meet the same mold in terms of outcomes.
So maybe there's a way around this issue of metrics which are kind of brittle and not necessarily what we actually want. Mm-hmm. There's a management approach called objectives and key results, which I think is used at Google. And the idea is to define what we want, say, from a subcontractor or from an employee or from a department or from a company from the point of view of society. At two levels. At one level, you have the objectives, which are like principles and are not necessarily very precise, but this is the spirit of the law. This is what you would like the organization to do. And then you have the key results, which are like metrics. There are things that are quantifiable and that the organization is going to try to stick to. But with the knowledge that these these metrics could change because maybe we find that they're not really sufficiently faithful to the high-level principles and objectives. And so you don't want them to overfit those metrics because they have to keep in mind that there's a higher principle that's at stake.
Yeah, I totally agree. And that's very much in line with the way that I've been thinking about these things too. And I think that these key results could sometimes be metrics or could sometimes be hitting the right process points.
Okay. I think we have 5 minutes remaining before the Q&A session. So the next topic is somewhat specific. End-to-end models or sequence-to-sequence models have been successfully applied to machine translation and speech recognition. Samsung is one of the first to apply them, actually. There had been a high expectation that dialogue system could be the next one to apply it, but it seems very difficult now. What field would be the next end-to-end model successful application area?
So I think what you're going to see, so end-to-end sort of really changed speech recognition because it allowed us to do speech recognition on device with the quality of the model in the server, but being much, much faster in terms of latency. And also the big thing is we don't have to be connected to the internet now. So basically we can do speech recognition on device without even having to be connected to the internet. So I think what you're going to see is because of that sort of breakthrough, the change I feel is in terms of what are the applications going to be going forward. So for example, I think you're going to see long meeting transcription, being able to having the end-to-end model always on your phone, being able to decode long meetings, long audio conversations. And particularly, how can you do this when the model needs to operate in low power and be always on? So this is one area I see. You can imagine now with COVID-19, you're going to want to do more audio-visual speech recognition. I'm bringing in multiple modalities, being able to do meeting transcription. It's going to be another area. Because we can do end-to-end ASR on device, offline, we don't need to log data.
Yes.
So things like federated learning, how can you train models on device with the data you have? How can you do personalized speech recognition for each individual user? It's going to be another area. And we have seen in some of our research that, we say one model to rule them all, so to speak, that having one model trained on multiple dialects or multiple languages seems to be, at least in small cases, work very well. How do we scale this up so we have one model for all languages in the world? Is going to be another challenging and interesting research area. So I see that end-to-end now is going to expand in many directions because of the new possibilities that it's opened up.
So I think that dialogue is very challenging because it sort of breaks the basic assumption of machine learning that you have a training set and a test set, and you can train on a training set and test on a test set.
Yes,
the dialogue systems are interactive, so the best way to train them is to train them with someone talking to them, presumably a large collection of people talking to the system, and you test it in similar situations. So there's been a very long-term project at Facebook called Parlay, P-A-R-L-A-I. There's a lot of open source code that came out of this project to kind of attempt to change the way we approach machine learning because of this interactivity. It makes everything more complicated. But of course, there is a huge demand for dialogue systems because we'd like to have intelligent virtual assistants, and that's what dialogue system can bring us. Now, there are probably useful dialogue systems that we can have in the near future that will not be able to answer like every question we can ask them, but they will be useful nevertheless. Before we have systems that are sufficiently intelligent that they're not frustrating to talk to, we'll have to have machines that have some level of common sense. And that's taking back to the questions we were discussing at the beginning of how is it that humans and animals accumulate so much background knowledge about the world in the first few months of life, and we can't reproduce this type of learning with machines. So all of those things are going to kind of converge at some point. Whether it's going to be in the next 2 years, 5 years, 10 years, 20 years, we don't know, because we don't know what techniques would be required for this for us to make significant progress in that direction.
Yes. Thank you, Dr. Lukun, and thank you all the panelists. I think it's time to go up to the next Q&A session. First of all, we have received a few questions in advance. The first question is from Sang-Yul Jeon. Are you there?
Yeah, hi.
Please say your name and affiliation first.
Hi, I'm Sang-Yul Jeon and currently PhD student at Yonsei University. And I have a question for In-Yeop Kang, corporate president. I noticed that the recent efforts of Samsung have focused on MPU solution for on-device deep learning. And recent studies on network compression have shown impressive results achieving higher speed at lower power. So as a graduate student studying software algorithms, I'm curious about the practical difficulties in implementing this into real hardware MPU.
Yeah, my mind is occupied with the fundamental challenges our friends are confronting, generalization, worldview, everything. And then, so compared to those challenging ones, I think how to implement efficiently, that's relatively easy. Let me put it that way. So especially on the mobile side, we've been working on mobile and data center, and we have a bunch of horsepowers. And then one thing we can do is we come up with the kinetic algorithms, and then we're trying to prune the network, and then we prune the bit width. We quantize it and distribute all over the computing engine we have, CPU, GPU, neural processor, DSP. And then also sometimes we sacrifice with the performance, so-called negligible performance degradation. So up to a certain point, like what Tara's working on, like end-to-end ASR, we could achieve a certain level right now. So we are comparable, but today idealized. our the researchers not comparable with the what's the next. That was interesting to me for today. All right.
Thank you.
Maybe I can add a little bit to your question.
Go ahead. Yeah.
I think that you will. How do you get these models to obey low latency? So we have all these great research ideas, but they have to fit within the latency constraints. They have to fit within the size constraints. They have to fit within the power constraints. And in the end, we try not to do all this model compression because we have to sacrifice on quality if we do. So what we do a lot of is try to either have specialized hardware so that we can run a lot of the models within the allowed latency constraints, especially like second pass rescore that I was talking about. A lot of that is hidden behind the first pass so it doesn't increase the latency. We try other things to reduce the latency of the model, like the endpointer I talked about. We try not to prune because then we will automatically take a degradation in quality. So looking at other ways to reduce latency is an area that our group has been pretty active in.
Thank you. Before we go to the next question, I have a short mention that Dr. Sung-woo Hwang, the president of SAIT and the co-chair of this program, is also connected in the session. So could you say hello? And no questions from you?
Comment and thank you to all of you. Thank you, Professor Benjio, for organizing all this forum again. And thank you, Professor Lee. You came back, you kept the promise. You told me you're gonna come back within 2 years. Thank you for coming back. And congratulations, Professor Finn, for Samsung AI Researcher of the Year. And I'd like to thank you, Tara and Jan, for your inspiring talk. Thank you very much. I think the role of co-chair of this forum is to serve you great dinner and wine, but this year I was not able to do that. I'm expecting next year. Thank you very much.
Yes, let's do the next year.
Also, thank you, IK, for participating in the panel. It was great.
Thank you, Dr. Hwang. So next question is from Igor Vasiljov. Are you connected?
Yes, I'm here. Can you hear me?
Yes.
Oh, great. Thank you so much for letting me ask the question. So my question is more general, maybe to all panelists. As we can see, recently many researchers in the AI field are focusing on the system 2, what is reasonable, as we all want to understand and trust the NN. However, as, for example, Professor Tara Sainat showed today, bringing some intentional bias can help for practical solutions. And bias is one of the known and inherited features of System 1. So my question is there any possibility to combine System 1 and System 2 in some smart way to get even higher practical performance? And when I say practical, please consider some limited energy budget solution. Thank you.
Any volunteer to answer this question?
Well, I think the question of bias in the sense that Tara was talking about is something that can apply at all levels. It's really about taking context into account and figuring out what the right context is that should influence the way that you're extracting features and processing them. So it's not specific to either System 1 or System 2.
Mm-hmm. Is it enough for you, Vasiljov?
Okay, we got it. That
but my general comment is the bias is already evil.
System 1.
I love zero bias.
We have to be
define
careful.
the bias. There's a difference.
Okay, yeah. The word bias means many different things, so we have to be careful.
Yeah,
yes,
sure.
Yes, bias in there.
So Jen would use the word bias in a different sense.
Right.
There's also a meaning that I use in my talk, which is inductive bias, which is a good thing, but it's a completely different concept.
In social bias, right? Okay. So let's move on to the next question. Sujong Kim has a question, I heard. Are you here?
Yeah. Hello, I'm Sujong, a PhD student at Seoul National University, and I have a question for Dr. Chara about her talk. According to the last experiment in the presentation, learning different kinds of Indian languages together performed better than learning them separately. So I wonder how the result could be different if the languages are totally different, as like Korean and English. So even in this case, will the co-training still help to increase the accuracy?
That's a great question. So in our research, we're finding that having one model trained on similar dialects or similar languages, then one model on all of these is better than a model in each individual domain. But when we scale this up to completely disjoint languages, we're not finding the same thing. And so basically, we're trying to look at injecting some sort of, or structuring the architecture to be more, let's say, language family specific now. Because just training on, let's say, 50 different languages, even with a very massively large network, we're not able to match the performance of each individual domain. So it's still an open and challenging research area.
Thank you.
Thank you. Now I would like to get an open Q&A from other online participants. If you have any questions to any panelist, please raise your hand. Okay, number 4. Yeah, Ida? You're right, Ida, right? Yeah, go ahead. You can start now.
Okay. Yeah, so thank you everyone for all your great talks. Earlier in the year at AAAI, there was an Oxford-style debate on whether AI researchers in academia should focus their attention on research problems that are not of immediate interest to industry. And maybe for our university researchers, it's really how you strike that balance, and a corollary, or like what are some of the things that you're working on that industry isn't focused on?
One example of this is the work that I presented on learning symmetries. That work is kind of very early stages and one of our initial forays into the direction of trying to extract symmetries and that sort of structure from data. I don't foresee it being immediately impactful to industry in its current form, but I think that in the longer term, these sorts of techniques may be actually quite useful and quite impactful on real world problems. So that's one example.
Any addition?
Another example I could mention is some of the work we're doing on causality, where at this stage we are only able to look at pretty small graphs with dozens of variables at most, we're testing it in environments that are very, very simple, far from the complexities that you would like in many real-world applications. Today, in reinforcement learning and many of these unsupervised sort of learning paradigms, you are typically working in simulated environments that are very, very simple, that have nothing of the complexities of the world, but still pose serious challenges. And I think it's going to take many years before we can grow the complexities of these environments to something closer to what applications need. On the other hand, I think the conceptual progress on understanding how you can build systems that are more robust, that can work out of distribution better, is of immediate application to industry, right? So, I can't presume what these things could be, but things like meta learning and in the right settings could be applied. But I'm thinking more broadly of techniques that can help. Examples that might have an impact fairly quickly could be new architectures that use attention or modularity or whatever. If these things work well in our little academic environments, there's a good chance they could also be applied in many industrial domains. But that is not the way that we're developing them. We're developing them in environments that are sufficiently under control and simple that we can debug and we can test theories and so on.
One other thing I'll add to this as well is a lot of the work that we do in robotics is on really basic motor skills, like playing with children's toys. And I don't expect robots that play with children's toys to be too useful or to be able to generate revenue, for example. But by studying those problems, we may be able to, in the future, discover fundamental challenges in artificial intelligence, which may lead to much kind of larger breakthroughs later down the line. It may allow us to better understand intelligence and what humans are capable of.
Okay, thank you. Any other question from the audience? If not, I will designate a questioner. Sung-wook Seo, are you there? Sung-wook Seo?
Yeah, I'm here.
Ask a question, please.
Hi, I'm Song Seo from Seoul National University, and I'd like to ask a question to Professor Chesterton. And first, thanks for the interesting work about the adaptive risk minimization, which seems to be more practical than other robot optimization work. But to my knowledge, this work assumes a test batch assumption where all test samples are drawn from a single group. So this might work well in some practical scenarios, like adapting the general model to a single end user. But however, there might be more realistic cases where we don't know the group information exactly at test time, and then unlabeled test samples can be drawn from multiple groups. So could you explain if this method still works in that case? And if not, how to deal with such heterogeneous test group samples for adaptation?
This is a great question, and the short answer is that this is an open problem and that we don't know how to solve yet. You're right in that the adaptive risk minimization framework is only going to be useful in settings where you expect to see unlabeled data from one part of the distribution, for example, from a new user, from a new region of the world, and so forth, which is often the case when you're kind of at a single point in time in a single place and you're seeing data from that part. But if your data is being shuffled, then we may need different frameworks for addressing that. It's also a problem that we're actively working on to try to address the parts of the distribution that our models are not good at and encourage the model to focus on those parts of the distribution so that it can improve on those more difficult examples. That said, I guess more speculatively, it may be that this sort of information about where in the distribution or where in the world you are is very important for models to do well. And the reason for this is that when humans take observations from the data, we see data in a very structured way. We see observations in time. We know the last observations that we saw. Things in time are very correlated. We're also always in the same place. The data that we're seeing are images. They aren't shuffled. We're always in one part of the world and in one point in time. And so it could be that to achieve the generalization that humans can achieve, we simply can't assume that all of our data is shuffled. We may need to make these sorts of assumptions that we're observing different parts of the distribution at different points in time. And that may allow us to achieve more robust models.
Thank you.
Okay. So do we have other questions from the audience? I see no hand there, so I would like to have the last question from Min-young Moon. Are you there? Say something, please. Oh, maybe some sound problem there.
You hear me now?
Okay, we hear now.
Okay, sorry about that.
Hello, I'm Min. I'm a researcher at SAIF. I read the paper of the hardware lottery, very interesting. And the paper introduces the terms called hardware lottery to describe when a research idea wins, not because the idea is superior to alternative research directions, but it is more suited to the variable software hardware. And I think deep neural network is actually a good example since, it was like introduced in 1980s. And, like back then it didn't really get much attention, but now, like it's everywhere, right? So my question is like, what will be the breakthrough of the modeling the world with the combination of hardware and software and algorithms? So to be more precise, like what will be the next hardware lotteries? Yeah, the question is to everyone.
The type of ideas that we have are very much limited by the type of tools that we have access to. So the idea, for example, that you can build a trainable system that is differentiable end-to-end by assembling modules is something that Yoshua and I have been playing since the early 90s, probably around 1991, 92. And it's been very powerful for us. And we were basically the only group who had access to a piece of software that was able to do this. Once Yoshua went to Montreal, he left AT&T and went to Montreal. He implemented in Montreal a system in C++ that could do the same thing, and then TNO, and then there was Torch and PyTorch. But the original system, we all had access to it all that. And it's one of the reasons I think that neural nets did not become more successful and more popular back in the 90s, is that having this tool, this type of tool, was very difficult. You had to kind of build it yourself. It required a huge investment, and few people were willing to do this. And as a result, few people were able to really kind of play with neural nets of the types that we are working today. I think what has changed is now it's become very commonplace, even for companies, to release all their code in open source. And that makes all the tools available to everyone. That's really what allowed deep learning to take off. That plus, of course, GPUs and the availability of our datasets, plus, a few new algorithms. But the fact that the tools, became available, very widely available, I think is really crucial. So hardware determines what we can do. GPUs were instrumental. Software also determines to some extent what ideas we authorize ourselves to think about. I'm going back even earlier in the history. Why is it that people didn't invent backpropagation back in the 1960s? It's a completely obvious idea when you think about it, right? It's just general, but people didn't think about it back then. It only started to be used for machine learning in the 1980s. And the reason is that people were using binary neurons. And the reason they were using binary neurons, there's several reasons, but one reason is it's very difficult with the hardware that you had at the time to compute weighted sums with neurons because multiplications were already expensive. If you had binary neurons, you didn't need to do multiplications, you just need to do addition and subtraction. And so the kind of hardware you have access to kind of limits your thinking. And good tools give you superpowers.
Thank you, Dr. Lukun. Any other?
And if I could add something, similarly today, I think the GPU architecture on which we depend may be forcing us into a style of computing that could close the doors to other types of architectures, for example, that involve a lot more sparsity. And dynamic routing of computation, for example. It in principle should allow you to save a lot of computation, but on a GPU-like chip, you don't save anything. In fact, it might be more expensive because of memory access issues.
That and batching also. GPUs force us to
basically
process multiple samples that are exactly the same size in parallel because it's easier to parallelize, but it's horrible. It's overly constraining if you're dealing with things like sequences of variable length, or graphs, or dynamical structures. So yeah, current hardware really doesn't do what we need it to do yet.
Thank you. And I think it's time to wrap up all the program of today. So now we have reached the end of the day one program of Samsung AI Forum 2020. I am deeply impressed by the great talks and insightful discussion. Thank you, all speakers and participants. Congratulations again to the awardees of Samsung AI Researchers of the Year. The Day 2 program of Samsung AI Forum will start at 9 a.m. tomorrow in Korean time. Goodbye now, and I hope to see you next year in person. Thank you.